How did black holes move from theory to reality? What lies beyond the event horizon? How do black holes shape the cosmos? In the vast expanse of our universe, there exist cosmic phenomena so mysterious and powerful that they challenge our very understanding of reality itself. These enigmatic entities, known as black holes, represent the ultimate extremes of nature, where matter is compressed to unimaginable densities and gravity becomes so intense that nothing, not even light, can escape their grasp. Black holes are cosmic paradoxes, invisible to our direct observation, yet their presence can be detected through the profound effects they exert on their surroundings. They are the universe's ultimate secret keepers, guarding the mysteries of space-time within their dark embrace. The concept of a black hole might seem like something from science fiction, but these extraordinary objects are very real, scattered throughout the cosmos. They come in various sizes, from relatively small, stellar mass black holes to the supermassive giants that lurk at the centers of galaxies, including our own Milky Way. When we gaze into the night sky, we are witnessing a universe shaped in countless ways by these invisible cosmic architects. They influence the formation of stars, the evolution of galaxies, and perhaps even the large-scale structure of the cosmos itself. To comprehend black holes is to push the boundaries of human knowledge to their limits. They represent a frontier where our current theories of physics break down, and new, more fundamental laws of nature may be waiting to be discovered. The journey to understand black holes has been a long and fascinating one, spanning centuries of scientific inquiry. It began not with telescopes or space probes, but with the human mind's capacity to imagine the impossible and question the known. In the late 18th century, the concept of what we now call black holes was first proposed by English geologist John Michell, who speculated about objects so massive and dense that their gravity would prevent light from escaping. This idea was largely forgotten for over a century, until it was independently rediscovered and developed further by Albert Einstein's theory of general relativity. Einstein's revolutionary theory, published in 1915, described gravity not as a force, but as a curvature of space-time caused by mass and energy. This new understanding of gravity opened the door to the possibility of black holes, though Einstein himself was initially skeptical about their physical existence. The mathematical foundations for black holes were laid by Carl Schwarzschild in 1916, just months after Einstein published his theory. While serving on the German front during World War I, Schwarzschild solved Einstein's field equations, finding a solution that described the gravitational field around a spherical mass. Schwarzschild's calculations revealed something extraordinary. If enough mass were compressed into a sufficiently small radius, it would create a region of space-time so severely warped that nothing could escape from it. This boundary, which we now call the event horizon, marks the point of no return. For decades after these theoretical predictions, black holes remained purely mathematical curiosities. Many physicists, including Einstein, doubted that such extreme objects could actually form in nature. It wasn't until the mid-20th century that scientific opinion began to shift. The term black hole itself was coined in 1967 by physicist John Wheeler, who helped popularize the concept and bring it into the mainstream of scientific discourse. By this time, astronomical observations were beginning to uncover evidence for objects that behaved exactly as black hole theories predicted. One of the first compelling pieces of evidence came from the discovery of quasars in the 1960s. These extremely bright and distant objects puzzled astronomers until it was realized that they could be explained by accretion disks around supermassive black holes. In the 1970s, the first strong candidate for a stellar mass black hole was identified, Cygnus X1, a powerful X-ray source in our galaxy. By studying the motion of a visible star orbiting an invisible companion, astronomers deduced that the companion must be extremely massive and compact, properties consistent with a black hole. Since then, technological advances have allowed us to detect black holes through various methods. We can observe their gravitational effects on nearby stars and gas, detect the X-rays emitted by matter as it spirals into them, and even measure the gravitational waves produced when black holes merge. The most direct evidence came in 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon. This groundbreaking achievement captured the shadow of the supermassive black hole at the center of the galaxy M87, providing visual confirmation of these cosmic enigmas. Today, black holes are no longer theoretical speculation, but an established component of our cosmic landscape. They are now studied extensively across multiple fields of physics and astronomy, offering unique insights into the fundamental nature of space, time, and gravity. At the heart of black hole physics lies Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by mass and energy. According to this theory, the more mass an object contains, the more it warps the space-time around it. Black holes represent the most extreme manifestation of this principle. When a massive star exhausts its nuclear fuel, it can no longer support its own weight against gravitational collapse. If the star is sufficiently massive, nothing can halt this collapse, and it continues to compress into an infinitely small point of infinite density known as a singularity. This singularity is surrounded by the event horizon, a spherical boundary in space-time that marks the point of no return. Once anything crosses this threshold, it is inevitably pulled toward the singularity, with no possibility of escape. The size of the event horizon is directly proportional to the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black hole at the center of our Milky Way galaxy, which has a mass of about 4 million times that of our Sun, the event horizon would extend to a radius of about 12 million kilometers. One of the most peculiar properties of black holes is their effect on time. According to Einstein's theory, time passes more slowly in strong gravitational fields. Near a black hole's event horizon, this time dilation becomes so extreme that, to an outside observer, time appears to nearly stop. Another fascinating aspect of black holes is their complete simplicity. Despite their complex formation and profound effects on their surroundings, black holes themselves are characterized by only 3 properties: mass, electric charge, and angular momentum. This is known as the no-hair theorem, which states that all other information about the matter that formed a black hole is lost behind the event horizon. The physics of black holes also leads to some of the most exotic phenomena in the universe. As matter falls toward a black hole, it forms an accretion disk, a swirling, superheated plasma that emits intense radiation, including X-rays and gamma rays. In some cases, particularly with rotating black holes, powerful jets of particles can be launched from the vicinity of the event horizon at nearly the speed of light. These jets can extend for thousands of light years and influence the surrounding intergalactic medium. The study of black holes has also led to profound theoretical insights, including the prediction of Hawking radiation, a theoretical process by which black holes can emit particles and gradually lose mass over time. This phenomenon, predicted by Stephen Hawking in 1974, connects quantum mechanics thermodynamics, and general relativity in unexpected ways. Perhaps the most defining feature of a black hole is its event horizon, the boundary beyond which nothing can escape. This invisible threshold marks the region where the escape velocity exceeds the speed of light, making it a one-way membrane in the fabric of space-time. The event horizon is not a physical surface, but rather a mathematical boundary in space-time. An object crossing it would not notice anything particularly peculiar at that exact moment, but it would be inexorably drawn toward the singularity at the center of the black hole. To an outside observer, however, the event horizon presents a fascinating spectacle. As an object approaches the event horizon, it appears to slow down and become increasingly redshifted due to the intense gravitational field. From the perspective of a distant observer, the object never quite reaches the event horizon, but instead appears to freeze at its surface, gradually fading from view. This apparent contradiction arises from the extreme distortion of space-time near a black hole. The intense gravity causes time to pass differently for observers at different distances from the event horizon, leading to these seemingly paradoxical observations. The size of the event horizon is determined by the mass of the black hole. For a non-rotating black hole, the radius of the event horizon, known as the Schwarzschild radius, is directly proportional to its mass. This relationship means that more massive black holes have larger event horizons, despite having the same extreme density. For rotating black holes, which are likely the most common type in the universe, the situation becomes more complex. The rotation causes the event horizon to bulge at the equator and creates an additional boundary called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Within the ergosphere, it's theoretically possible for objects to extract energy from the black hole's rotation through a process known as the Penrose process. This phenomenon allows particles to enter the ergosphere and emerge with more energy than they had initially, effectively mining the rotational energy of the black hole. The event horizon also plays a crucial role in the information paradox, a theoretical puzzle that has puzzled physicists for decades. According to quantum mechanics, information can never be destroyed, yet when matter falls into a black hole, it appears to be lost behind the event horizon, seemingly violating this fundamental principle. This paradox has led to intense debates and new theoretical developments, including the holographic principle, which suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space, in this case, the event horizon. Recent theoretical work has proposed that the event horizon might not be the smooth, featureless boundary once imagined, but could instead be a firewall of high-energy particles. This radical idea challenges our understanding of black hole physics and the equivalence principle, a cornerstone of general relativity. The event horizon also marks the boundary of our current knowledge. What happens beyond this threshold remains one of the greatest mysteries in physics, as our current theories break down in the extreme conditions near the singularity. Despite these mysteries, the event horizon serves as a crucial testing ground for theories of quantum gravity, which attempt to reconcile general relativity with quantum mechanics. By studying the properties of event horizons, physicists hope to gain insights into a more fundamental theory of nature. As we continue to explore the cosmos and develop more sophisticated tools for observing black holes, we inch closer to unraveling the secrets of these cosmic enigmas. Each discovery brings new questions and challenges our understanding of the universe, reminding us that the cosmos still holds many mysteries waiting to be discovered. To truly grasp the profound nature of black holes, we must first understand the very fabric in which they exist and manipulate. Space-time, the fundamental structure of our universe, is a concept that challenges our everyday perceptions of reality. It is the four-dimensional continuum that combines the three dimensions of space with the one dimension of time into a single, interwoven fabric. This cosmic tapestry forms the stage upon which all cosmic events unfold, including the dramatic influence of black holes. The concept of space-time was revolutionized by Albert Einstein in the early 20th century, fundamentally changing our understanding of gravity. Before Einstein, gravity was viewed as a mysterious force acting instantaneously across vast distances, pulling objects toward one another. Einstein's theory of general relativity reimagined gravity not as a force, but as the curvature of space-time itself, caused by mass and energy. This elegant explanation transformed our perception of the universe from a mechanical system to a dynamic, geometric structure. Imagine space-time as a vast, invisible fabric stretched across the cosmos, with celestial objects creating indentations or curves in this fabric. The more massive an object, the deeper the curve it creates in space-time. These curves guide the movement of other objects, which we perceive as gravitational attraction. In this view, Earth orbits the Sun, not because of a mysterious pulling force, but because it follows the curved path created by the Sun's mass in the fabric of space-time. The curvature of space-time is not merely an abstract mathematical concept. It has measurable effects that we can observe in our universe. One of the most famous confirmations of Einstein's theory came during a solar eclipse in 1919, when astronomers observed that starlight passing near the Sun was bent by its gravitational field. This bending of light, known as gravitational lensing, occurs because light follows the curved paths in space-time created by massive objects. Space-time is not static, but dynamic, responding to the presence of mass and energy by warping and flexing. When massive objects move or accelerate, they create ripples in space-time that propagate outward at the speed of light. These ripples, known as gravitational waves, were predicted by Einstein in 1916, but not directly detected until nearly a century later, in 2015, by the Laser Interferometer Gravitational Wave Observatory, LIGO. The detection of gravitational waves marked a monumental breakthrough in physics, providing direct evidence for the dynamic nature of space-time. These waves are generated by some of the most violent events in the universe, such as the collision of black holes or neutron stars. When two black holes spiral toward each other and merge, they create ripples in space-time that travel across the cosmos, carrying information about their origins and nature. Space-time is not uniform throughout the universe. Its properties can vary depending on the local gravitational field. In regions of strong gravity, such as near a black hole, time itself slows down relative to regions of weaker gravity. This phenomenon, known as time dilation, has been experimentally verified and is even accounted for in the global positioning system, which must adjust for the different flow of time experienced by satellites in orbit compared to observers on Earth. The relationship between space and time in the fabric of space-time is intricate and inseparable. As one moves through space, one also moves through time, and the faster one travels through space, the slower one moves through time. This interconnection becomes particularly pronounced at velocities approaching the speed of light, where relativistic effects become significant and our intuitive notions of space and time break down. Black holes represent the most extreme distortions of space-time in the universe, creating regions where the curvature becomes so severe that the fabric itself appears to tear. At the center of a black hole lies the singularity, a point where space-time curvature becomes infinite and our current laws of physics break down. The singularity is surrounded by the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. The event horizon of a black hole is not a physical surface, but rather a boundary in space-time, where the escape velocity equals the speed of light. Within this region, space-time is so severely warped that all possible paths lead inward toward the singularity. From the perspective of an outside observer, an object falling into a black hole appears to slow down and fade from view as it approaches the event horizon, never quite crossing it within any finite observation time. Space-time near a black hole exhibits properties that seem to defy our everyday understanding of reality. As one approaches the event horizon, the gravitational time dilation becomes so extreme that, to a distant observer, time appears to nearly stop. This effect has profound implications for our perception of events near black holes and raises fascinating questions about the nature of time itself. The extreme curvature of space-time around a black hole also leads to other peculiar phenomena, such as the formation of accretion disks. As matter falls toward a black hole, it forms a swirling disk of superheated gas that orbits at nearly the speed of light. The intense gravitational forces and friction within this disk cause it to emit enormous amounts of radiation, making some black holes among the brightest objects in the universe despite their inherent darkness. The study of space-time has led to some of the most profound insights in modern physics, connecting seemingly unrelated concepts in unexpected ways. One of the most remarkable developments is the holographic principle, which suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space. This radical idea implies that our three-dimensional universe might be a holographic projection of information stored on a distant two-dimensional surface. Quantum mechanics, our theory of the very small, and general relativity, our theory of the very large, offer fundamentally different descriptions of space-time. While general relativity portrays space-time as smooth and continuous, quantum mechanics suggests that at the smallest scales, space-time might be grainy and discrete. Reconciling these disparate views into a unified theory of quantum gravity remains one of the greatest challenges in theoretical physics. The quest to understand space-time has led physicists to explore some of the most exotic and mind-bending concepts imaginable. These include wormholes, theoretical tunnels through space-time that could connect distant regions of the universe, white holes, hypothetical objects that are the time reverse of black holes, and cosmic strings, one-dimensional defects in space-time that could have formed in the early universe. While these ideas remain speculative, they represent the frontiers of our exploration into the nature of reality. The fabric of space-time is not merely a passive stage for cosmic events, but an active participant in the evolution of the universe. Through the curvature of space-time, matter and energy tell space-time how to curve, and curved space-time tells matter and energy how to move. This dynamic interplay shapes the large-scale structure of the cosmos, from the formation of galaxies to the expansion of the universe itself. As we contemplate the nature of space-time, we are confronted with questions that touch upon the deepest mysteries of existence. What is the fundamental nature of reality? Why does our universe have three spatial dimensions and one time dimension? What lies beyond the event horizon of a black hole? These questions remind us that despite our tremendous progress in understanding the cosmos, the universe still holds profound secrets waiting to be discovered. The exploration of space-time continues to drive innovation in both theoretical and experimental physics. Advanced telescopes observe the most distant reaches of the universe, probing the effects of space-time curvature on cosmic scales. Sophisticated experiments test the limits of our current theories, searching for deviations that might point to new physics. And theoretical physicists develop mathematical frameworks that push the boundaries of human imagination, seeking to describe the fundamental nature of reality. The concept of space-time has also permeated popular culture, inspiring countless works of science fiction that explore its implications and possibilities. From time travel to faster-than-light travel, from parallel universes to wormholes, the imaginative exploration of space-time has captured the public imagination and sparked interest in the profound questions raised by modern physics. Yet, despite our familiarity with the concept of space-time, it remains one of the most elusive and mysterious aspects of our universe. We can describe its properties mathematically and observe its effects, but its fundamental nature continues to challenge our understanding. As we delve deeper into the mysteries of space-time, we may find that our current conceptions are merely approximations of a reality far stranger and more wonderful than we can imagine. The study of space-time has revealed that our universe is not only stranger than we imagine, but stranger than we can imagine. It is a realm where time can slow down and speed up, where space can stretch and warp, and where the familiar rules of everyday experience give way to phenomena that seem to defy logic. In this cosmic tapestry, black holes stand as the most extreme manifestations of space-time curvature, challenging our understanding and inviting us to explore the deepest mysteries of the cosmos. As we continue our journey into the nature of space-time, we find ourselves drawn ever deeper into the mysteries of black holes and their profound effects on the fabric of reality. The interplay between space-time and these cosmic enigmas reveals a universe of breathtaking complexity and beauty, inviting us to contemplate our place within its vast expanse. The exploration of space-time is not merely an academic pursuit, but a deeply human endeavor to understand the fundamental nature of reality itself. In the vast cosmic tapestry, stars are born, live out their lives, and eventually meet their end in a variety of spectacular ways. The most massive stars among them experience a fate so extraordinary that it challenges our understanding of physics itself. These stellar giants, many times heavier than our Sun, burn through their nuclear fuel at a furious pace, consuming millions of years' worth of energy in just a few million years. Their lives are a race against time, as the nuclear fusion that sustains them battles against the relentless crush of gravity. When a massive star has exhausted its nuclear fuel, a delicate balance that has maintained its stability for millions of years suddenly collapses. For most of a star's life, the outward pressure generated by nuclear fusion perfectly counteracts the inward pull of gravity, creating a state of equilibrium. But when the fuel runs out, gravity begins to win this cosmic tug-of-war, and the star's core begins to contract under its own immense weight. This contraction accelerates as the core grows denser and hotter, reaching temperatures and pressures that defy our everyday comprehension. As the core continues to collapse, the star's outer layers may be expelled in a brilliant explosion known as a supernova, visible across vast cosmic distances. These cosmic fireworks are among the most energetic events in the universe, briefly outshining entire galaxies and dispersing heavy elements into space. Yet, for the most massive stars, even this dramatic explosion is not the end of the story. While the outer layers are blown away, the core continues its inexorable collapse, crushed by gravity that grows stronger as the matter becomes more densely packed. The core of a collapsing massive star is transformed into an object of such extreme density that a teaspoon of its material would weigh billions of tons on Earth. This unimaginable compression continues until the matter reaches a state where atoms themselves are crushed, their electrons forced into protons to form neutrons. For a moment, the collapse may be halted by the pressure of these densely packed neutrons, creating what astronomers call a neutron star. These objects are so dense that they can contain more mass than our Sun within a sphere only about 20 kilometers across. But for the most massive stars, even neutron degeneracy pressure cannot withstand the crushing force of gravity. When the core's mass exceeds about 3 times that of our Sun, no known force in the universe can prevent the complete collapse of matter. The core continues to contract, reaching densities so extreme that our current understanding of physics breaks down. At this point, the matter collapses into a point of infinite density, known as a singularity, marking the birth of one of the universe's most mysterious phenomena, a black hole. The formation of a black hole is a process that occurs behind a veil of cosmic secrecy, hidden from direct observation by the very nature of the phenomenon. As the singularity forms, an event horizon begins to take shape around it, creating a boundary in space-time beyond which nothing can escape. This event horizon grows as more matter falls into the newly formed black hole, establishing the region where the laws of physics, as we know them, cease to apply in their familiar form. The birth of a black hole represents a transformation so profound that it tears the fabric of space-time itself. The collapse of a massive star into a black hole is not an instantaneous event, but a process that unfolds over time, though from our perspective it may appear quite rapid. As matter crosses the event horizon, it carries with it information about its previous state, leading to profound questions about the nature of information in the universe. These questions touch upon some of the deepest mysteries in physics, challenging our understanding of the fundamental laws that govern reality. The formation of a black hole is thus not just a physical process, but a philosophical one, raising questions about the nature of space, time, and information itself. The newly formed black hole immediately begins to exert its influence on the surrounding space, warping the fabric of space-time in its vicinity. This warping creates a gravitational field so intense that nothing, not even light, can escape once it crosses the boundary of the event horizon. The black hole's presence can be detected through its effects on nearby matter and light, even though the object itself remains invisible to direct observation. These effects provide astronomers with clues about the black hole's mass, rotation, and other properties, allowing us to study these enigmatic objects indirectly. The birth of a black hole from stellar collapse is one of the most extreme events in the universe, representing the ultimate triumph of gravity over all other forces. It is a process that transforms matter from a state we can comprehend into one that challenges our understanding of physics itself. The collapse releases enormous amounts of energy in the form of neutrinos and gravitational waves, ripples in space-time that propagate outward at the speed of light. These gravitational waves, predicted by Einstein's theory of general relativity, provide a unique window into the violent processes that create black holes. The study of stellar collapse and black hole formation has been revolutionized by recent advances in astronomical observation and theoretical physics. Sophisticated computer simulations allow scientists to model the complex processes involved in stellar collapse, providing insights into the mechanisms that drive these cosmic events. At the same time, gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, capturing the faint ripples in spacetime produced by the formation and merger of black holes. These observations have confirmed many theoretical predictions, while also raising new questions about the nature of these extreme phenomena. The conditions necessary for black hole formation are found only in the most massive stars, typically those with more than 20 times the mass of our Sun. Stars below this threshold face different fates, ending their lives as white dwarfs or neutron stars rather than black holes. This threshold is not absolute, however, as factors such as rotation, magnetic fields, and the star's chemical composition can influence its final fate. The study of these factors helps astronomers understand the diversity of stellar endpoints and the conditions that lead to the formation of black holes. The process of stellar collapse and black hole formation is not merely a theoretical construct, but a reality that has been observed throughout the universe. Astronomers have identified numerous stellar mass black holes in our galaxy and beyond, detected through their interactions with companion stars or the radiation emitted by matter falling into them. These observations confirm that the process of stellar collapse and black hole formation is an ongoing phenomenon in the cosmos, playing a crucial role in the evolution of the universe, role in the evolution of galaxies and the universe as a whole. Each discovery brings us closer to understanding these cosmic enigmas and their place in the grand tapestry of the universe. The birth of a black hole marks the beginning of a new phase in the evolution of matter, one that is hidden from direct view but profoundly influences the surrounding space. The newly formed black hole immediately begins to interact with its environment, potentially accreting matter from a companion star or the surrounding interstellar medium. This accretion process can create some of the most luminous objects in the universe as matter spirals inward, forming an accretion disk that heats to extreme temperatures and emits intense radiation across the electromagnetic spectrum. The formation of a black hole through stellar collapse is a process that connects the smallest scales of physics to the largest structures in the universe. It involves the fundamental forces of nature, working under conditions of extreme density and temperature, pushing our understanding of physics to its limits. At the same time, the resulting black holes can grow to become supermassive objects that influence the evolution of entire galaxies, creating a cosmic connection between the microscopic and the macroscopic. This interplay between scales highlights the profound unity of the universe and the fundamental laws that govern its behavior. The study of black hole formation has also led to insights into the nature of spacetime itself, revealing how extreme concentrations of mass can warp the fabric of reality. These warps in spacetime affect the motion of nearby objects and the path of light passing through the region, creating observable effects that confirm Einstein's theory of general relativity. The detection of these effects provides some of the strongest evidence for the existence of black holes and our understanding of their properties. Each observation adds to our knowledge of these cosmic phenomena, gradually unveiling the secrets they hold. The birth of a black hole represents a transformation so profound that it challenges our understanding of the nature of matter and energy. It is a process that takes matter from a state we can study and comprehend to one that exists beyond the limits of our current physical theories. This transformation raises fundamental questions about the nature of reality and the limits of human knowledge, reminding us that the universe still holds mysteries beyond our current understanding. As we continue to study these cosmic phenomena, we are not just learning about black holes, but also exploring the fundamental nature of reality itself. The formation of black holes through stellar collapse is a process that has been occurring throughout the history of the universe. From the first generation of stars to the present day, each black hole formation event contributes to the cosmic inventory of these mysterious objects, influencing the evolution of galaxies and the distribution of matter in the universe. Over cosmic time, these processes have shaped the universe we observe today, creating a complex tapestry of structures and phenomena that reflect the underlying physical laws. The study of black hole formation is thus not just an investigation of specific objects, but an exploration of the universe's history and evolution. The birth of a black hole is a cosmic event that bridges the gap between the life and death of stars, marking the end of one cosmic journey and the beginning of another. It is a process that transforms matter from a state that has existed for millions of years into something entirely new and mysterious. This transformation is not just physical, but conceptual, challenging our understanding of the universe and our place within it. As we contemplate the formation of black holes, we are confronted with the profound mysteries of the cosmos and the limits of human knowledge, inviting us to explore further into the unknown. The journey of a star from its birth to its ultimate fate is a cosmic story that spans millions or even billions of years. Stars begin their lives as vast clouds of gas and dust in space, known as nebulae, which slowly collapse under their own gravitational pull. As these clouds contract, they begin to spin and heat up, eventually reaching temperatures and pressures high enough to ignite nuclear fusion in their cores. This fusion process, where hydrogen atoms combine to form helium, releases tremendous amounts of energy and marks the birth of a new star, which will now shine for millions or billions of years. The life of a star is a delicate balance between two opposing forces: gravity, pulling inward, and the pressure from nuclear fusion, pushing outward. This balance, known as hydrostatic equilibrium, determines how long a star will live and how it will eventually die. Stars with masses similar to our Sun will live for about 10 billion years, fusing hydrogen into helium in their cores, before eventually expanding into red giants and ending their lives as white dwarfs. These relatively peaceful endings are in stark contrast to the dramatic fates that await the most massive stars in the universe. Massive stars, those with more than about 8 times the mass of our Sun, live very different lives than their smaller counterparts. They burn through their nuclear fuel at a furious rate, consuming millions of years' worth of energy in just a few million years. Their intense gravity creates higher temperatures and pressures in their cores, allowing them to fuse elements beyond hydrogen and helium, creating carbon, oxygen, and even heavier elements through successive stages of nuclear fusion. This process of creating heavier elements is what provides the universe with the building blocks necessary for planets and life itself. As a massive star continues to fuse heavier elements in its core, it creates an onion-like structure, with different layers of elements being fused at different temperatures and pressures. The outermost layer consists of hydrogen, followed by helium, then carbon, oxygen, and increasingly heavier elements toward the core. Each stage of fusion produces less energy than the previous one, while the star's gravity continues to compress the core further. This cycle continues until the star begins to fuse iron in its core, which marks the beginning of the end for the massive star. Iron is unique among the elements because fusing it does not release energy, but instead requires energy input. When a massive star's core begins to fuse iron, it can no longer generate the outward pressure needed to counteract the crushing force of gravity. The core begins to collapse under its own weight, triggering a chain reaction that will ultimately lead to the star's explosive death. This collapse happens in a matter of seconds, as the core, which may have been roughly the size of Earth, shrinks to a size smaller than a city, reaching densities that are nearly incomprehensible. The core collapse of a massive star is one of the most extreme events in the universe, reaching temperatures of billions of degrees and densities greater than that of an atomic nucleus. Under these conditions, protons and electrons are crushed together to form neutrons and neutrinos in a process known as neutronization. The neutrinos, which are nearly massless particles that rarely interact with matter, carry away most of the energy from the collapse, while the neutrons form an incredibly dense core. This neutron core briefly resists further collapse, creating a shockwave that propagates outward through the star. The shockwave created by the core bounce is what causes the star to explode in a brilliant supernova, one of the most energetic events in the universe. This explosion blows off the star's outer layers, creating an expanding cloud of gas and dust that will eventually seed the surrounding space with heavy elements. These elements, created during the star's lifetime and during the supernova explosion itself, will become part of new stars, planets, and even living organisms in a cosmic cycle of death and rebirth. The supernova explosion can outshine an entire galaxy for a brief period, making it visible across vast cosmic distances. What remains after the supernova explosion depends on the mass of the original star's core. If the core mass is less than about 3 times the mass of our Sun, it will settle into a neutron star, an incredibly dense object composed almost entirely of neutrons. A neutron star with the mass of our Sun would be only about 20 kilometers in diameter, yet contain more mass than our entire solar system combined. These objects are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth, making them among the most extreme objects in the universe. For the most massive stars, however, even neutron degeneracy pressure cannot withstand the crushing force of gravity. If the core mass exceeds about 3 times the mass of our Sun, no known force in the universe can prevent the complete collapse of matter. The core continues to contract, reaching densities so extreme that our current understanding of physics breaks down. At this point, the matter collapses into a point of infinite density, known as a singularity, marking the birth of one of the universe's most mysterious phenomena, a black hole. The formation of a black hole from a massive star's core is a process that occurs behind a veil of cosmic secrecy, hidden from direct observation by the very nature of the phenomenon. As the singularity forms, an event horizon begins to take shape around it, creating a boundary in spacetime beyond which nothing can escape. This event horizon grows as more matter falls into the newly formed black hole, establishing the region where the laws of physics as we know them cease to apply in their familiar form. The birth of a black hole represents a transformation so profound that it tears the fabric of space-time itself. The study of stellar evolution and black hole formation has been revolutionized by recent advances in astronomical observation and theoretical physics. Sophisticated computer simulations allow scientists to model the complex processes involved in stellar collapse, providing insights into the mechanisms that drive these cosmic events. At the same time, gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, capturing the faint ripples in space-time produced by the formation and merger of black holes. These observations have confirmed many theoretical predictions, while also raising new questions about the nature of these extreme phenomena. The conditions necessary for black hole formation are found only in the most massive stars. typically those with more than 20 times the mass of our Sun. Stars below this threshold face different fates, ending their lives as white dwarfs or neutron stars rather than black holes. This threshold is not absolute, however, as factors such as rotation, magnetic fields, and the star's chemical composition can influence its final fate. The study of these factors helps astronomers understand the diversity of stellar endpoints and the conditions that lead to the formation of black holes. The process of stellar evolution and black hole formation is not merely a theoretical construct, but a reality that has been observed throughout the universe. Astronomers have identified numerous stellar mass black holes in our galaxy and beyond, detected through their interactions with companion stars or the radiation emitted by matter falling into them. These observations confirm that the process of stellar evolution leading to black hole formation is an ongoing phenomenon in the cosmos, playing a crucial role in the evolution of galaxies and the universe as a whole. Each discovery brings us closer to understanding these cosmic enigmas and their place in the grand tapestry of the universe. The formation of black holes through stellar evolution represents a critical link in the cosmic cycle of matter and energy. Massive stars fuse lighter elements into heavier ones throughout their lives, and when they die, they return these elements to the universe through supernova explosions. The black holes that remain from these stellar deaths continue to influence their surroundings, potentially accreting more matter and growing over time. This process of growth and evolution continues over cosmic timescales, with some stellar mass black holes eventually merging with others to form even larger black holes. The study of stellar evolution has revealed that the first generation of stars in the universe, known as population 3 stars, were likely different from the stars we see today. These primordial stars, formed from the pristine hydrogen and helium created in the Big Bang, without the heavier elements that characterize later generations of stars. Theoretical models suggest that these first stars were extremely massive, possibly hundreds of times the mass of our Sun, and would have lived short, violent lives before ending as black holes. These early black holes may have served as seeds for the supermassive black holes that now reside at the centers of galaxies. The connection between stellar evolution and black hole formation extends beyond individual stars to influence the evolution of entire galaxies. Black holes formed from stellar deaths can grow over time through accretion and mergers, eventually becoming the supermassive black holes found at the centers of most galaxies. These supermassive black holes, in turn, influence the formation and evolution of their host galaxies through feedback mechanisms that regulate star formation. This intricate relationship between black holes and galaxies represents one of the most fascinating areas of modern astrophysics, revealing the deep connections between the smallest and largest structures in the universe. The diversity of black holes formed through stellar evolution reflects the complexity of the processes involved in their creation. Not all stellar mass black holes are identical. They can vary in mass, spin, and other properties depending on the characteristics of their progenitor stars and the specific conditions of their formation. Some black holes may be nearly non-rotating, while others spin at nearly the speed of light. Some may form in isolation, while others are part of binary systems where they interact with companion stars. This diversity provides astronomers with a rich tapestry of phenomena to study, each offering unique insights into the nature of black holes and the physics of extreme gravity. The study of stellar evolution and black hole formation has also led to insights into the nature of space-time itself. revealing how extreme concentrations of mass can warp the fabric of reality. These warps in spacetime affect the motion of nearby objects and the path of light passing through the region, creating observable effects that confirm Einstein's theory of general relativity. The detection of these effects provides some of the strongest evidence for the existence of black holes and our understanding of their properties. Each observation adds to our knowledge of these cosmic phenomena, gradually unveiling the secrets they hold. The formation of black holes through stellar evolution is a process that has been occurring throughout the history of the universe, from the first generation of stars to the present day. Each black hole formation event contributes to the cosmic inventory of these mysterious objects, influencing the evolution of galaxies and the distribution of matter in the universe. Over cosmic time, these processes have shaped the universe we observe today, creating a complex tapestry of structures and phenomena that reflect the underlying physical laws. The study of stellar evolution and black hole formation is thus not just an investigation of specific objects, but an exploration of the universe's history and evolution. The connection between stellar evolution and black hole genesis represents a profound link between the life cycles of stars and the most extreme objects in the universe. It is a process that transforms matter from a state we can study and comprehend to one that exists beyond the limits of our current physical theories. This transformation raises fundamental questions about the nature of reality and the limits of human knowledge, reminding us that the universe still holds mysteries beyond our current understanding. As we continue to study these cosmic phenomena, we are not just learning about black holes, but also exploring the fundamental nature of reality itself. The birth of a black hole through stellar evolution marks the end of one cosmic journey and the beginning of another, creating an object that will continue to influence its surroundings for billions of years. These stellar remnants serve as cosmic laboratories where the laws of physics are tested under conditions of extreme gravity, density, and temperature. They challenge our understanding of the universe and push the boundaries of human knowledge, inviting us to explore further into the mysteries of the cosmos. As we contemplate the formation of black holes through stellar evolution, we are confronted with the profound interconnectedness of the universe and the elegant simplicity of the physical laws that govern its behavior. In the vast cosmic landscape, black holes come in various sizes, each with its own unique characteristics and origins. These cosmic entities range from relatively small objects formed by the collapse of individual stars to colossal giants that lurk at the centers of galaxies. The diversity of black holes reflects the different processes that create them and the various environments in which they exist. Understanding these different types of black holes provides us with a more complete picture of their role in shaping the cosmos and the fundamental physics that governs their behavior. The most common type of black hole is the stellar mass black hole, formed when a massive star exhausts its nuclear fuel and collapses under its own gravity. These black holes typically contain between about 5 and 50 times the mass of our Sun, compressed into a region of space smaller than a city. Despite their relatively small size, stellar mass black holes exert gravitational forces so intense that nothing, not even light, can escape their pull once it crosses the event horizon. These objects are often found in binary systems, where they orbit a companion star and slowly draw matter from their stellar partner. Stellar mass black holes are scattered throughout galaxies, including our own Milky Way, and serve as cosmic laboratories for testing our understanding of extreme gravity. Astronomers have identified numerous stellar mass black holes in our galaxy by observing their effects on nearby stars and the X-rays emitted by matter as it spirals into them. One of the most well-known examples is Cygnus X1, discovered in 1964, which was one of the first strong candidates for a black hole, and has since become a crucial object of study for astrophysicists. These relatively small black holes provide valuable insights into the processes that occur near the event horizon and the behavior of matter under extreme gravitational conditions. Between the stellar mass black holes and the supermassive giants lies a mysterious category known as intermediate mass black holes. These elusive objects, with masses ranging from about 100 to 100,000 times that of our Sun, have proven difficult to detect and confirm. Their existence was long theorized, but only recently supported by observational evidence, as they occupy a mass range that is not easily explained by current models of black hole formation. The discovery of intermediate mass black holes has opened new questions about how black holes grow and evolve over cosmic time. Intermediate mass black holes may form through several mechanisms, including the merger of smaller stellar mass black holes or the collapse of extremely massive stars in the early universe. Some theories suggest that these objects could serve as seeds for the supermassive black holes found at the centers of galaxies, gradually accumulating mass over billions of years. The detection of intermediate mass black holes has been challenging because they do not always produce the telltale signs associated with other black holes, such as bright accretion disks or gravitational waves. However, recent advances in observational technology have allowed astronomers to identify several promising candidates, bringing us closer to understanding this enigmatic class of cosmic objects. At the opposite end of the spectrum from stellar mass black holes are the supermassive black holes, true cosmic giants that can contain millions or even billions of times the mass of our Sun. These enormous objects reside at the centers of most, if not all, large galaxies, including our own Milky Way, which hosts a supermassive black hole named Sagittarius, a star, with a mass of about 4 million times that of our Sun. The presence of supermassive black holes at galactic centers suggests a deep connection between the formation and evolution of galaxies and these cosmic behemoths. The gravitational influence of supermassive black holes extends far beyond their immediate vicinity, affecting the motion of stars and the distribution of matter throughout their host galaxies. Supermassive black holes grow through a combination of accretion, consuming surrounding gas and dust, and merges with other black holes during galactic collisions. As matter falls toward a supermassive black hole, it forms an accretion disk that heats to extreme temperatures and emits intense radiation across the electromagnetic spectrum. In some cases, this process creates quasars, among the brightest objects in the universe, which can outshine their entire host galaxies. The energy released by accretion onto supermassive black holes can regulate star formation in their galaxies through feedback mechanisms, creating a delicate balance that influences the evolution of cosmic structures over billions of years. The formation of supermassive black holes presents a significant challenge to our understanding of the early universe, as they must have grown to their enormous sizes relatively quickly after the Big Bang. Some supermassive black holes observed at great distances, and therefore seen as they were in the early universe, have masses comparable to those found in nearby galaxies. This suggests that they must have accumulated mass at rates that strain our current models of black hole growth and accretion. Several theories have been proposed to explain this rapid growth, including the direct collapse of massive gas clouds in the early universe, or the existence of initially massive seed black holes that formed through processes not commonly observed today. Beyond the stellar mass, intermediate mass, and supermassive categories, theoretical physics predicts the existence of even more exotic types of black holes. Primordial black holes, for example, are hypothetical objects that could have formed in the extreme conditions of the early universe, not from stellar collapse, but from the gravitational collapse of dense regions of matter. These primordial black holes could theoretically have a wide range of masses, from microscopic to many times that of our Sun, depending on when and how they formed. While no primordial black holes have been definitively detected, they remain an intriguing possibility that could help explain certain cosmological phenomena, such as dark matter or the gravitational wave events observed by detectors like LIGO and Virgo. Another theoretical category is that of micro black holes, which would have masses much smaller than stellar mass black holes and sizes comparable to subatomic particles. These objects, if they exist, could potentially be created in high-energy particle collisions or through quantum fluctuations in spacetime. Some theories suggest that micro black holes might evaporate almost instantly through a process called Hawking radiation, proposed by Stephen Hawking in 1974, which allows black holes to lose mass over time. The search for evidence of micro black holes and the study of Hawking radiation represent frontiers in theoretical physics that could help reconcile general relativity with quantum mechanics. The diversity of black holes in the universe reflects the rich tapestry of physical processes that govern cosmic evolution. Each type of black hole, from the smallest theoretical entities to the largest supermassive giants, offers unique insights into the nature of gravity, space-time, and the extreme conditions that exist in our universe. The study of these different types of black holes has revealed connections between seemingly unrelated phenomena and has pushed the boundaries of our understanding of the physical world. As our observational capabilities continue to improve, we are likely to discover even more variety in the population of black holes, further expanding our knowledge of these cosmic enigmas. The classification of black holes by mass is not merely a matter of academic interest, but has profound implications for our understanding of the universe. Different types of black holes form through different mechanisms, exist in different environments, and influence their surroundings in distinct ways. Stellar mass black holes, for example, are often associated with the death throes of massive stars and the production of heavy elements, while supermassive black holes play a crucial role in the evolution of galaxies. By studying the full spectrum of black holes, astronomers and physicists can piece together a more comprehensive picture of cosmic evolution and the physical laws that govern it. The existence of black holes across such a wide range of masses also raises fundamental questions about the nature of gravity and the structure of spacetime. Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, has been remarkably successful in predicting and explaining the behavior of black holes. However, the extreme conditions near black hole singularities, where density becomes infinite and our current theories break down, suggest that a more fundamental theory may be needed. The study of different types of black holes provides a testing ground for theories that attempt to unify general relativity with quantum mechanics, potentially leading to a deeper understanding of the fundamental nature of reality. As we continue to explore the cosmos and detect more black holes across the mass spectrum, we are likely to uncover new mysteries and challenges to our current understanding. The recent detection of gravitational waves from merging black holes has opened a new window on the universe, allowing us to observe these cosmic events in ways previously impossible. Each new discovery adds to our knowledge, while also raising new questions, reminding us that the universe still holds many secrets waiting to be revealed. The study of black holes, in all their varied forms, represents one of the most exciting frontiers in modern science, promising to reshape our understanding of the cosmos in ways we can scarcely imagine. In the heart of every black hole lies a mystery so profound that it challenges the very foundations of physics as we know it. This mysterious core, known as a singularity, represents a point where matter is compressed to infinite density within zero volume, creating conditions that defy our current understanding of the universe. At the singularity, the curvature of spacetime becomes infinite, and the laws of physics, as we understand them, cease to apply. It is a realm where our most successful theories, general relativity and quantum mechanics, both fail to provide meaningful descriptions of reality. The concept of a singularity first emerged from the equations of Einstein's general relativity, which describe gravity as the curvature of space-time caused by mass and energy. When these equations are applied to extremely massive objects, they predict that under certain conditions, matter can collapse to a point of infinite density. This prediction was initially seen as a mathematical curiosity rather than a physical reality, even by Einstein himself, who found the idea troubling. However, as our understanding of black holes evolved, the existence of singularities became an unavoidable consequence of the theory, forcing physicists to confront the limitations of our current understanding. What makes singularities so perplexing is that they represent a breakdown of the physical laws that have proven remarkably successful in describing the rest of the universe. General relativity, which has been confirmed by countless observations and experiments, simply cannot describe what happens at the singularity. The equations produce infinite values for quantities like density and curvature, which in physics usually indicates that the theory has reached its limits of applicability. This breakdown suggests that a more fundamental theory is needed to describe these extreme conditions, one that could potentially unify general relativity with quantum mechanics. The search for such a theory has been one of the holy grails of theoretical physics for decades, with numerous approaches proposed to resolve the singularity problem. Some theories suggest that quantum effects might prevent the formation of true singularities, replacing them with extremely dense but finite objects, often called fuzzballs or quantum stars. Other approaches, like string theory, propose that singularities might be resolved in higher dimensions, or that what appears as a singularity in our three-dimensional space might have a more complex structure in a higher dimensional reality. These ideas remain speculative, but they represent attempts to extend our understanding beyond the limits of current theories. One of the most puzzling aspects of singularities is their apparent violation of the principle of determinism, which states that the state of a system at one time should determine its state at all future times. At a singularity, this principle breaks down because the equations of physics cease to provide unique predictions about what happens to matter that reaches this point. This loss of predictability is deeply troubling to physicists, as it suggests that the universe might not be as orderly and deterministic as we have long believed. The singularity problem thus challenges not only our technical understanding of physics, but also our philosophical conception of how the universe operates. The nature of singularities also raises profound questions about the conservation of information, a fundamental principle in quantum mechanics. According to quantum theory, information can never be destroyed, only transformed or transferred. However, when matter falls into a black hole and reaches the singularity, it appears that the information it carries might be lost forever, creating what is known as the information paradox. This paradox has generated intense debate among physicists for decades, with some arguing that information must somehow be preserved, perhaps through subtle quantum effects at the event horizon, while others suggest that our understanding of information conservation might need to be revised in the context of black holes. Another fascinating aspect of singularities is their relationship to the structure of space-time itself. In general relativity, space-time is not merely a passive stage on which physical events unfold, but an active participant that responds to the presence of mass and energy. At a singularity, this relationship becomes extreme, with space-time becoming so severely distorted that our usual notions of space and time lose their meaning. The singularity represents a point where the fabric of space-time itself appears to tear, creating a hole in the structure of reality as we understand it. This tearing of space-time challenges our most basic intuitions about the nature of the universe and our place within it. The study of singularities has also led to some of the most exotic and mind-bending concepts in theoretical physics, including wormholes, time machines, and the possibility of multiple universes. Some theories suggest that certain types of singularities might be connected to other regions of space-time through tunnels known as wormholes, potentially allowing for shortcuts through space or even time travel. Other ideas propose that singularities might be gateways to other universes, forming a complex network of interconnected cosmic realms. While these concepts remain highly speculative, they illustrate how the study of singularities pushes the boundaries of human imagination and theoretical exploration. One of the most intriguing questions about singularities is whether they actually exist in physical reality or are merely artifacts of our incomplete understanding of physics. The extreme conditions at a singularity are so far beyond anything we can observe or experiment with in laboratories that we must rely on mathematical models and theoretical reasoning to explore them. This limitation means that our understanding of singularities is inherently provisional, subject to revision as new theories and observations emerge. The singularity problem thus serves as a humbling reminder of the limits of human knowledge and the vast mysteries that still await discovery in the universe. The search for a resolution to the singularity problem has driven some of the most innovative and creative work in theoretical physics. Researchers have developed numerous approaches, from loop quantum gravity to string theory to causal dynamical triangulation, each attempting to reconcile general relativity with quantum mechanics and eliminate the infinities that appear at singularities. These approaches often involve radical reimagining of the fundamental nature of reality, suggesting that space and time might not be continuous but discrete, or that the universe might have more dimensions than we perceive. While none of these theories has yet been definitively confirmed, they represent the cutting edge of our attempt to understand the deepest mysteries of the cosmos. Perhaps the most profound implication of singularities is what they reveal about the limits of human knowledge and the nature of scientific inquiry. The existence of singularities in our most successful theories of physics suggests that there are realms of reality that lie beyond our current capacity to comprehend. This realization is both humbling and exhilarating, reminding us that despite all we have learned about the universe, there are still frontiers to explore and mysteries to unravel. The study of singularities thus represents not just a technical challenge for physicists, but a deeply human endeavor to push the boundaries of understanding and glimpse the fundamental nature of reality. As we continue to explore the mysteries of singularities, we are reminded that the universe is often stranger and more wonderful than we can imagine. The quest to understand these enigmatic points of infinite density has led to some of the most profound insights in modern physics, connecting seemingly disparate concepts in unexpected ways. It has revealed deep connections between gravity and quantum mechanics, between information and thermodynamics, and between the structure of space-time and the nature of reality itself. Each step forward in understanding singularities brings new questions and challenges, ensuring that this field will remain at the forefront of scientific inquiry for generations to come. The study of singularities also has important implications for our understanding of the origin and fate of the universe. According to the Big Bang theory, the universe began in a state of extremely high density and temperature, similar to a singularity. If singularities are indeed real physical phenomena, then the Big Bang might represent a similar kind of space-time singularity, raising questions about what came before the universe and how it emerged from such a state. These questions touch upon some of the deepest mysteries of existence, connecting the physics of black holes to the ultimate origins of the cosmos and our place within it. In the end, the singularity remains one of the most tantalizing mysteries in modern physics, a frontier where our current understanding reaches its limits and new physics must emerge. It represents a challenge to our most fundamental theories and intuitions about reality, inviting us to imagine beyond the boundaries of what is known. As we continue to explore this cosmic enigma, we are not just learning about black holes, but also probing the deepest foundations of physics itself, seeking to understand the fundamental laws that govern our universe. The journey to unravel the mystery of the singularity is a journey into the heart of reality itself, a quest that promises to transform our understanding of the cosmos in ways we can scarcely imagine. In the mysterious realm surrounding black holes, time itself behaves in ways that challenge our everyday understanding of reality. The phenomenon known as time dilation, predicted by Einstein's theory of general relativity, becomes profoundly pronounced in the vicinity of these cosmic enigmas. According to this theory, time does not flow at a constant rate throughout the universe, but instead varies depending on the strength of the gravitational field. In regions of intense gravity, such as near a black hole, time passes more slowly relative to regions of weaker gravity, creating a temporal landscape that is as warped as the space around it. The concept of time dilation can be difficult to grasp, as it contradicts our intuitive sense of time as a universal constant that ticks away at the same rate for everyone, everywhere. Yet experiments have confirmed that time dilation is a real physical phenomenon, measurable even in Earth's relatively weak gravitational field. For instance, clocks at higher altitudes, where gravity is slightly weaker, run slightly faster than clocks at lower altitudes. This effect, though minuscule on Earth, becomes dramatically amplified near black holes, where gravity is so intense that it can stretch time to nearly infinite proportions. As an object approaches a black hole, the gravitational time dilation becomes increasingly extreme. To a distant observer, a clock falling toward a black hole would appear to tick progressively slower as it approaches the event horizon. At the event horizon itself, time appears to stop completely from the perspective of an outside observer. This creates the strange spectacle of seeing objects frozen in time at the edge of a black hole, never quite crossing the event horizon within any finite observation period, even though from the perspective of the falling object, it continues to accelerate inward. This apparent paradox arises because time is not absolute, but relative, depending on the observer's frame of reference and the strength of the gravitational field they experience. For an astronaut falling into a black hole, time would continue to pass normally from their perspective, and they would cross the event horizon without noticing anything particularly peculiar at that exact moment. However, once across this threshold, their fate is sealed, as they will inevitably be pulled toward the singularity at the center of the black hole, with no possibility of escape or return. The extreme time dilation near black holes has profound implications for how we observe and understand these cosmic phenomena. When we observe matter falling into a black hole, we see it appear to slow down and fade from view as it approaches the event horizon. The light emitted by this matter becomes increasingly redshifted due to the intense gravitational field, stretching to longer wavelengths and eventually becoming undetectable. This creates an observational veil that hides the most extreme regions of black holes from direct view, challenging astronomers to develop indirect methods to study these enigmatic objects. Gravitational time dilation also affects the perception of events near black holes in ways that can seem to defy logic. For example, if we could observe a star being consumed by a black hole, we would see the process appear to slow down as the star approaches the event horizon. The final moments of the star's destruction, from our perspective, would be stretched out over an extremely long period, potentially making it appear as though the star never completely disappears. This temporal distortion creates a cosmic illusion that masks the violent reality of what is happening at the event horizon. The relationship between black holes and time dilation extends beyond the immediate vicinity of these objects to influence our understanding of the universe on larger scales. The extreme time dilation near black holes provides a unique testing ground for general relativity, allowing physicists to verify predictions about how gravity affects the flow of time. These tests have consistently confirmed Einstein's theory, while also revealing new insights into the nature of spacetime and the behavior of matter under extreme conditions. Each observation of time dilation near black holes adds another piece to the puzzle of how gravity shapes the fabric of reality. One of the most fascinating aspects of time dilation near black holes is its connection to the concept of causality, the idea that cause must precede effect. In the warped space-time around a black hole, the relationship between cause and effect can become distorted in ways that challenge our conventional understanding. The extreme curvature of space-time can create paths through space-time where the temporal order of events appears reversed from certain perspectives. While this does not violate causality in a fundamental sense, it does illustrate how black holes can bend the rules that govern the behavior of time and space. The study of time dilation near black holes has also led to insights into the nature of information and its preservation in the universe. As matter falls into a black hole, the extreme time dilation at the event horizon raises questions about what happens to the information contained in that matter. Does it disappear forever beyond the event horizon, or is somehow preserved in the distorted space-time around the black hole? These questions touch upon some of the deepest mysteries in physics, connecting the behavior of time near black holes to fundamental principles of quantum mechanics and information theory. The effects of time dilation become even more pronounced for rotating black holes, which drag space-time around with them in a phenomenon known as frame dragging. This rotation creates an additional layer of complexity to the temporal landscape around black holes, with time flowing at different rates, depending not only on the distance from the black hole, but also on the direction of movement relative to the black hole's rotation. In the ergosphere, a region outside the event horizon of a rotating black hole, space-time itself is dragged around so forcefully that all objects must co-rotate with the black hole, creating a temporal vortex that defies our usual notions of space and time. The mathematical description of time dilation near black holes involves complex equations from general relativity that describe how the curvature of space-time affects the flow of time. These equations predict that the time dilation factor becomes infinite at the event horizon, meaning that time effectively stops from the perspective of a distant observer. This mathematical result has profound implications for our understanding of black holes, suggesting that the event horizon represents a boundary where the flow of time, as we know it, ceases to exist. The study of these equations has revealed deep connections between the geometry of space-time and the behavior of time itself. Observational evidence for time dilation near black holes comes from various sources, including the study of X-ray emissions from matter orbiting black holes. As matter spirals inward in an accretion disk, it emits X-rays that can be detected by space-based telescopes. The analysis of these emissions shows the effects of gravitational time dilation, with the timing of X-ray pulses slowed in a manner consistent with general relativity's predictions. These observations provide some of the strongest evidence for the extreme distortion of time near black holes, confirming theoretical predictions with remarkable precision. The phenomenon of time dilation near black holes also has implications for the long-term evolution of these cosmic objects. From the perspective of a distant observer, the formation of a black hole appears to take an infinite amount of time, as the final collapse of matter beyond the event horizon is stretched out indefinitely due to time dilation. This creates a curious situation where, in principle, we never actually see a black hole form, even though we know they must exist based on their gravitational effects on surrounding matter. This apparent paradox highlights the complex relationship between observation and reality in the context of extreme gravitational fields. The study of time dilation near black holes has practical applications for our understanding of the universe and the development of new technologies. For example, the precise measurement of time dilation effects is crucial for the operation of global positioning systems, which must account for the difference in the flow of time between satellites in orbit and receivers on Earth. Similarly, the study of extreme time dilation near black holes informs the development of theories that attempt to unify general relativity with quantum mechanics, potentially leading to breakthroughs in our understanding of the fundamental nature of reality. Perhaps the most profound implication of time dilation near black holes is what it reveals about the nature of time itself. The fact that time can flow at different rates, depending on the strength of gravity, suggests that time is not an absolute background against which events unfold, but an integral part of the fabric of space-time. This realization has transformed our understanding of the universe, replacing the Newtonian view of time as a universal constant with the relativistic view of time as a dynamic and flexible component of reality. The study of time dilation near black holes continues to push the boundaries of this understanding, revealing new layers of complexity in the relationship between time, space, and gravity. As we contemplate the extreme distortion of time near black holes, we are reminded of the profound mystery that these cosmic enigmas represent. The behavior of time in the vicinity of black holes challenges our most basic intuitions about reality, inviting us to imagine a universe where the familiar rules of cause and effect no longer apply in their usual form. This exploration of time near black holes is not merely an academic exercise, but a journey into the deepest mysteries of the cosmos, revealing the strange and wonderful nature of the universe we inhabit. Each insight into the behavior of time near black holes brings us closer to understanding the fundamental architecture of reality and our place within it. As we journey deeper into the mysteries of black holes, we encounter one of the most peculiar and fascinating phenomena associated with these cosmic enigmas. This effect, whimsically named spaghettification, describes the extreme stretching and compression that objects experience as they venture too close to a black hole. The term itself paints a vivid picture of matter being elongated into thin strands, much like spaghetti, as it falls toward the event horizon. This process is not merely a theoretical curiosity, but a real physical consequence of the intense gravitational forces at work near black holes. The phenomenon of spaghettification arises from tidal forces, which are differences in gravitational pull across an object. In everyday life, we experience tidal forces in a much gentler form through the moon's gravitational effect on Earth's oceans, creating tides. Near a black hole, however, these tidal forces become exponentially stronger, creating a gravitational gradient so extreme that the pull on the side of an object closest to the black hole can be vastly stronger than the pull on the far side. This differential force stretches the object lengthwise, while simultaneously compressing it sideways, creating the characteristic spaghettification effect. What makes spaghettification particularly fascinating is how it depends on the size of the black hole. Counterintuitively, smaller black holes actually produce more extreme tidal forces than larger ones at their event horizons. This is because the event horizon of a smaller black hole is much closer to its central singularity, where the gravitational gradient is steeper. For a stellar mass black hole, the tidal forces near the event horizon would be so extreme that they would tear apart any object before it even crosses the threshold. In contrast, near a supermassive black hole, the event horizon is so far from the singularity that an object might cross it without immediately experiencing destructive tidal forces. The physics behind spaghettification involves the fundamental nature of gravity, as described by Einstein's theory of general relativity. According to this theory, gravity is not a force acting at a distance, but rather the curvature of spacetime caused by mass and energy. Near a black hole, this curvature becomes so extreme that it creates the intense gravitational gradients responsible for spaghettification. The mathematics describing this phenomenon is complex, involving solutions to Einstein's field equations that predict how objects will behave in the highly curved spacetime around a black hole. As an object falls toward a black hole, it experiences increasing tidal forces that first become noticeable, then uncomfortable, and ultimately lethal. For a human being, or any complex organism, the process would begin with a gentle pulling sensation, much like being stretched in opposite directions. As the object continues its descent, this stretching would become more pronounced, eventually causing structural failure as molecules and atoms are pulled apart. The final stages of spaghettification involve the complete disintegration of matter into its constituent particles as they spiral toward the singularity. The spaghettification process affects different types of matter in different ways, depending on their structural integrity and composition. Gases and liquids, being more fluid, would deform more easily than solid objects, which might resist the tidal forces until they reach a critical threshold. Similarly, objects with stronger molecular bonds would withstand the stretching longer than those with weaker bonds. This differential effect means that as an object falls into a black hole, it would not simply stretch uniformly, but would likely experience complex patterns of deformation and disruption as its various components respond differently to the tidal forces. One of the most intriguing aspects of spaghettification is how it relates to the concept of the Roche limit, which describes the distance within which a celestial body held together only by its own gravity will disintegrate due to tidal forces. While the Roche limit is typically discussed in the context of planets and moons orbiting stars, a similar principle applies to objects approaching black holes. The difference is that near a black hole, the tidal forces become so extreme that they can overcome not just gravitational binding, but the much stronger electromagnetic and nuclear forces that hold matter together. This makes black holes uniquely capable of completely dismantling the structure of matter itself. The study of spaghettification provides valuable insights into the nature of gravity and the behavior of matter under extreme conditions. By analyzing how objects respond to the intense tidal forces near black holes, physicists can test the predictions of general relativity and probe the limits of our understanding of gravity. These studies have consistently confirmed Einstein's theory, while also revealing new aspects of how matter behaves in the most extreme gravitational environments in the universe. Each observation of tidal effects near black holes adds another piece to our understanding of these cosmic enigmas. From an observational standpoint, the effects of spaghettification can be detected through the analysis of radiation emitted by matter as it falls into black holes. As matter is stretched and heated by tidal forces, it emits X-rays and other forms of high-energy radiation that can be detected by space-based telescopes. These emissions provide astronomers with a window into the violent processes occurring near black holes, allowing them to study the properties of both the black holes and the matter being consumed. The analysis of these emissions has revealed complex patterns of radiation that reflect the extreme physical processes at work. The mathematical description of spaghettification involves concepts from differential geometry, which allow physicists to calculate how objects will deform in the curved spacetime around a black hole. These calculations show that the stretching effect increases exponentially as an object approaches the event horizon, with the length of the object growing without bound, while its width decreases proportionally. This mathematical framework has been extensively tested through computer simulations, which model the behavior of various types of matter falling into black holes. These simulations have provided detailed predictions about the spaghettification process that can be compared with observational data. One of the most fascinating aspects of spaghettification is how it affects the perception of time for an object falling into a black hole. As we discussed earlier, time dilation becomes extreme near black holes, causing time to pass more slowly for the falling object relative to a distant observer. When combined with the effects of spaghettification, this creates a complex interplay between the spatial and temporal dimensions that defies our usual understanding of reality. The falling object would experience time normally from its own perspective, even as it is being stretched to extreme lengths, while to a distant observer, the entire process would appear to slow down and freeze at the event horizon. The phenomenon of spaghettification also has implications for the information paradox that we touched upon earlier. As matter is stretched and pulled apart by tidal forces, the information it contains becomes distributed along the length of the spaghettified object. This raises questions about whether this information is preserved in some form or lost forever as the matter crosses the event horizon. The resolution of this question has profound implications for our understanding of quantum mechanics and the fundamental nature of information in the universe. It represents one of the deepest connections between the physics of black holes and the quantum realm. The effects of spaghettification extend beyond the immediate vicinity of black holes to influence the surrounding space in various ways. The intense tidal forces can disrupt the orbits of nearby stars and planets, potentially ejecting them from their galactic neighborhoods or sending them into the galactic void, them spiraling toward the black hole. These disruptions can create observable effects that astronomers use to identify and study black holes, even when they cannot be seen directly. The study of these tidal disruptions has revealed that black holes play a crucial role in shaping the dynamics of stellar systems and galaxies. In the context of stellar evolution, spaghettification represents the final fate of stars that venture too close to black holes. When a star passes within the tidal radius of a black hole, It is torn apart by the extreme gravitational forces, with some of its material falling into the black hole and the rest being ejected at high velocities. These tidal disruption events are among the most violent phenomena in the universe, releasing enormous amounts of energy in the form of radiation, and sometimes creating observable jets of particles moving at nearly the speed of light. The study of these events has provided valuable insights into the properties of both black holes and the stars that fall victim to them. The theoretical framework describing spaghettification has been extended to include the effects of quantum mechanics, creating a more complete picture of how matter behaves near black holes. Quantum effects become particularly important as matter approaches the singularity, where the classical description of gravity breaks down. These quantum corrections to the spaghettification process suggest that at extremely small scales, matter might behave in ways that are not predicted by classical general relativity. This area of research represents one of the frontiers in theoretical physics, where the quest to unify general relativity with quantum mechanics is actively pursued. The study of spaghettification also has implications for the search for a theory of quantum gravity, which would reconcile general relativity with quantum mechanics. By examining how matter behaves under the extreme conditions near black holes, physicists can test the predictions of various candidate theories of quantum gravity. These tests have placed constraints on possible theories while also highlighting areas where our current understanding is incomplete. The phenomenon of spaghettification thus serves as a bridge between the macroscopic world, described by general relativity, and the microscopic world, described by quantum mechanics. As we contemplate the extreme effects of spaghettification near black holes, we are reminded of the profound mystery that these cosmic enigmas represent. The violent stretching and compression of matter near black holes challenges our understanding of the fundamental forces of nature and the structure of matter itself. This exploration of tidal effects near black holes is not merely an academic exercise, but a journey into the deepest mysteries of the cosmos, revealing the strange and wonderful nature of the universe we inhabit. Each insight into the behavior of matter near black holes brings us closer to understanding the fundamental architecture of reality and our place within it. In the depths of black hole physics lies a puzzle so profound that it challenges the very foundations of our understanding of the universe. This puzzle, known as the information paradox, strikes at the heart of the conflict between two of our most successful physical theories, quantum mechanics and general relativity. At its core, the paradox asks a seemingly simple question: what happens to information that falls into a black hole? The answer to this question has far-reaching implications for our understanding of reality, touching upon the fundamental nature of information, time, and the universe itself. To appreciate the paradox, we must first understand what physicists mean by information in this context. In quantum mechanics, information is more than just data. It is the complete description of a system, including the quantum states of all its particles. According to the principles of quantum mechanics, information can never be destroyed, only transformed or transferred. This principle, known as unitarity, is fundamental to quantum theory and has been confirmed by countless experiments. It suggests that the evolution of quantum systems is reversible in principle, meaning that knowing the final state of a system should, in theory, allow us to reconstruct its initial state. The conflict arises when we consider what happens to information that falls into a black hole according to general relativity. As we've discussed, matter that crosses the event horizon of a black hole is inevitably pulled toward the singularity at its center. According to classical general relativity, this matter, along with all the information it contains, is crushed out of existence at the singularity. From this perspective, the information is simply destroyed, violating the quantum mechanical principle that information must be preserved. This contradiction between quantum mechanics and general relativity creates the information paradox. The paradox was sharpened in 1974 when Stephen Hawking discovered that black holes are not entirely black, but can emit radiation through a quantum process now known as Hawking radiation. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs can spontaneously form from the vacuum. Normally, these pairs would quickly annihilate each other, but near the event horizon, one particle might fall into the black hole while the other escapes, carrying energy away from the black hole. Over time, this process causes the black hole to lose mass and eventually evaporate completely. Hawking's discovery added a new dimension to the information paradox. If a black hole evaporates completely through Hawking radiation, what happens to the information that fell into it? The radiation itself appears to be purely thermal, meaning it carries no information about what fell into the black hole beyond its mass, charge, and angular momentum. This suggests that when the black hole finally evaporates, the information that fell into it is irretrievably lost, again violating the quantum principle of information conservation. This became known as the black hole information paradox, and it has puzzled physicists for decades. The implications of the information paradox extend far beyond black holes themselves. If information can indeed be destroyed in black holes, this would require a fundamental revision of quantum mechanics, potentially undermining one of the most successful theories in the history of physics. On the other hand, if information is preserved, this would require a modification of general relativity to allow information to escape from black holes in some way. Either outcome would represent a profound shift in our understanding of the universe and the laws that govern it. The resolution of this paradox thus holds the key to a deeper understanding of the fundamental nature of reality. Over the years, numerous attempts have been made to resolve the information paradox, each proposing a different mechanism by which information might be preserved. One early suggestion was that information might escape through subtle correlations in the Hawking radiation itself, making the radiation not purely thermal after all. This idea, however, faced significant technical challenges and was initially met with skepticism. Another proposal suggested that information might be preserved in a remnant left behind after the black hole evaporates, though this raised questions about the nature of such remnants and how they could store the information. A significant development came in the 1990s with the proposal of the holographic principle by Gerard 't Hooft and later developed by Leonard Susskind. This principle suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space. In the context of black holes, this would mean that the information about what falls into a black hole is somehow encoded on its event horizon, much like a hologram encodes three-dimensional information on a two-dimensional surface. This radical idea offered a new way of thinking about the relationship between information, space, and black holes. The holographic principle led to the development of the ADS/CFT correspondence, a conjectured relationship between gravitational theories in certain types of spaces and quantum field theories on their boundaries. This correspondence, proposed by Juan Maldacena in 1997, provided a concrete mathematical framework for the holographic principle and suggested a possible resolution to the information paradox. According to this view, the physics of a black hole in a higher dimensional space is equivalent to a quantum field theory without gravity on its boundary. In this framework, information never falls into the black hole in the first place, but is always represented on the boundary. Another approach to resolving the information paradox involves the idea of black hole complementarity. proposed by Leonard Susskind and others. This principle suggests that the experience of an observer falling into a black hole and that of an observer watching from outside are both valid but complementary descriptions of reality, much like the wave-particle duality in quantum mechanics. From this perspective, information is both reflected at the event horizon and passes through it, with no single observer seeing both descriptions simultaneously. This idea attempts to reconcile the seemingly contradictory experiences of different observers in the vicinity of a black hole. In recent years, the firewall paradox has added another layer of complexity to the information puzzle. Proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, this argument suggests that if information is to escape from a black hole, there must be a firewall of high-energy particles at the event horizon. This firewall would be disastrous for anyone falling into the black hole, as they would be instantly incinerated upon reaching the event horizon. The firewall paradox highlights the deep tensions between different principles in physics, and suggests that resolving the information paradox may require radical new ideas about the nature of black holes and spacetime itself. One of the most recent developments in the quest to resolve the information paradox involves the concept of quantum entanglement and its relationship to spacetime geometry. This line of research suggests that the entanglement of quantum particles might be intimately connected to the structure of spacetime itself, with entanglement essentially weaving the fabric of spacetime together. In the context of black holes, this would mean that the quantum entanglement between particles inside and outside the event horizon plays a crucial role in preserving information. This approach, known as IT from qubit, represents a promising new direction in the search for a resolution to the information paradox. The information paradox has also inspired new experimental approaches, even though direct experiments with black holes remain beyond our current technological capabilities. Instead, physicists have turned to analog systems that mimic certain aspects of black hole physics, such as sonic black holes in fluid systems or optical black holes in nonlinear media. These analog systems allow researchers to study phenomena analogous to Hawking radiation and potentially gain insights into the information paradox. While these analogies have limitations, they provide valuable testing grounds for theoretical ideas about black holes and information. The resolution of the information paradox would have profound implications for our understanding of the universe and potentially lead to a unified theory of quantum gravity. Such a theory would reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the behavior of particles at the smallest scales. The information paradox thus serves as a guide pointing toward deeper theories that might unify our understanding of the fundamental forces of nature. It represents one of the most important frontiers in theoretical physics, where the quest for knowledge pushes the boundaries of human understanding. As we contemplate the information paradox, we are reminded of the profound mystery that black holes represent and the deep questions they raise about the nature of reality. The paradox challenges us to think beyond our current theories and imagine new ways of understanding the universe. It connects seemingly disparate areas of physics, from quantum mechanics to general relativity to information theory, revealing deep underlying unity in the fundamental laws of nature. The resolution of this paradox, when it comes, will likely transform our understanding of the universe in ways we can scarcely imagine today. The information paradox also raises philosophical questions about the nature of reality and our ability to comprehend it. If information is indeed fundamental to the universe, as many physicists now believe, then understanding how information behaves in the most extreme conditions becomes crucial to understanding reality itself. The paradox suggests that at the deepest level, the universe might be fundamentally informational in nature, with physical reality emerging from the processing of information. This idea, while speculative, represents a radical shift in how we think about the universe and our place within it. As research continues into the information paradox, new ideas and approaches continue to emerge, each offering a different perspective on this profound puzzle. Some physicists suggest that the resolution might require a complete rethinking of quantum mechanics or general relativity, while others believe that a synthesis of existing theories might suffice. What is clear is that the information paradox represents one of the deepest challenges in theoretical physics, and its resolution will likely involve insights that are currently beyond our imagination. The quest to resolve this paradox is a journey into the unknown, driven by our human desire to understand the fundamental nature of reality. The study of the information paradox has also led to unexpected connections between black hole physics and other areas of physics, including quantum computing and condensed matter physics. These connections have revealed that the physics of black holes is not an isolated field, but is deeply intertwined with many other areas of research. The cross-pollination of ideas between these fields has led to new insights and approaches, enriching our understanding of both black holes and the seemingly unrelated systems they connect to. This interconnectedness highlights the unity of physics and the power of fundamental research to drive innovation across multiple disciplines. As we continue to explore the information paradox, we are reminded that the universe is often stranger and more wonderful than we can imagine. The paradox challenges our most basic assumptions about reality, inviting us to consider possibilities that defy our everyday intuition. It represents a frontier of human knowledge, where the known meets the unknown, and where the quest for understanding drives us to push the boundaries of what is possible. The resolution of the information paradox, when it comes, will not only answer a specific question about black holes, but will likely transform our understanding of the universe in profound and unexpected ways. In the vast cosmic tapestry, black holes remain among the most enigmatic objects, invisible to direct observation, yet betraying their presence through subtle clues scattered across the universe. Detecting these cosmic phantoms requires astronomers to become cosmic detectives, piecing together evidence from various sources to reveal the hidden giants lurking in the depths of space. The challenge of detecting black holes has driven the development of increasingly sophisticated observational techniques, each providing a different window into these mysterious phenomena. Through these methods, scientists have transformed black holes from theoretical curiosities into established components of our cosmic landscape. One of the primary methods for detecting black holes involves observing their gravitational influence on nearby objects, particularly stars. When a black hole and a star orbit each other in what is known as a binary system, the star's motion reveals the presence of its invisible companion. Astronomers can measure the star's velocity and orbital characteristics to calculate the mass of the unseen object, determining whether it is dense enough to be a black hole. This technique has been remarkably successful in identifying stellar mass black holes throughout our galaxy, providing some of the most compelling evidence for their existence. The dance of stars around invisible partners has unveiled a hidden population of black holes scattered across the Milky Way. Another powerful detection method involves observing the X-rays emitted by matter as it spirals into a black hole. When gas and dust from a companion star or the surrounding environment fall toward a black hole, they form an accretion disk that heats to extreme temperatures due to friction and gravitational compression. This superheated matter emits intense radiation, particularly in the X-ray portion, of the electromagnetic spectrum, which can be detected by space-based telescopes. These X-ray emissions serve as cosmic beacons, announcing the presence of a black hole even when the object itself remains invisible. The study of these X-ray signatures has revealed not only the existence of black holes, but also details about their mass, spin, and accretion processes. The detection of gravitational waves has opened an entirely new window on the universe, allowing scientists to observe black holes in ways previously impossible. When two black holes spiral toward each other and merge, they create ripples in the fabric of spacetime itself, propagating outward at the speed of light. These gravitational waves, predicted by Einstein's theory of general relativity a century ago, were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LYGO. This groundbreaking discovery confirmed a major prediction of general relativity and inaugurated the field of gravitational wave astronomy, providing a completely new method for studying black holes and their properties. Each gravitational wave detection offers unique insights into the masses, spins, and merger dynamics of black hole pairs. The Event Horizon Telescope project represents one of the most ambitious efforts to directly observe black holes, or at least their immediate surroundings. This global collaboration links together radio telescopes across the Earth to create a virtual telescope the size of our planet, capable of resolving details as small as the event horizon of a supermassive black hole. In 2019, the Event Horizon Telescope team released the first ever image of a black hole's shadow, capturing the silhouette of the supermassive black hole at the center of the galaxy M87 against the glowing backdrop of its accretion disk. This historic achievement provided visual confirmation of black holes and allowed scientists to test general relativity in extreme gravitational environments. The image, resembling a dark circle surrounded by a ring of light, captured the imagination of people worldwide and marked a milestone in our exploration of these cosmic enigmas. Astronomers also detect black holes through their influence on the larger scale structure of galaxies. Supermassive black holes, residing at the centers of galaxies, can profoundly affect their host galaxies through feedback mechanisms, regulating star formation and influencing the distribution of matter. By studying the properties and evolution of galaxies, scientists can infer the presence and characteristics of central black holes, even when direct observation is impossible. This approach has revealed a surprising correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, suggesting a deep connection between the evolution of black holes and their host galaxies. These galactic-scale observations have transformed our understanding of how black holes shape the cosmos on the grandest scales. Quasars, among the brightest objects in the universe, serve as distant beacons signaling the presence of supermassive black holes in the early universe. These brilliant sources of radiation are powered by accretion onto supermassive black holes, with the infalling matter converting gravitational energy into electromagnetic radiation with extraordinary efficiency. The study of quasars has revealed that supermassive black holes existed when the universe was less than 1 billion years old, challenging our understanding of how these objects could have formed so quickly after the Big Bang. Each quasar, detected across cosmic distances, provides information about the early universe and the growth of black holes over cosmic time. These cosmic lighthouses continue to illuminate our understanding of black hole formation and evolution. The detection of black holes through microlensing effects offers another clever method for identifying these elusive objects. When a black hole passes between us and a distant star, its gravitational field can bend and magnify the starlight, creating a temporary brightening known as a microlensing event. By monitoring millions of stars for these telltale brightenings, astronomers can detect black holes that would otherwise remain invisible, including isolated black holes not accompanied by companion stars. This technique has proven particularly valuable for finding black holes that are not actively accreting matter and therefore do not emit X-rays or other detectable radiation. Microlensing surveys have revealed a population of black holes wandering through the galaxy, unseen but not unfelt. Jets of high-energy particles shooting out from the vicinity of black holes provide another signature of their presence. These relativistic jets, which can extend for thousands of light years, are formed by complex processes involving the black hole's rotation and magnetic fields. When these jets are pointed toward Earth, they appear as bright sources of radiation known as blazars, which can be detected across the electromagnetic spectrum. The study of these jets has revealed important information about the physics of black hole accretion and the mechanisms by which black holes can launch material at nearly the speed of light. Each jet observed offers clues about the properties of its parent black hole and the extreme conditions in its immediate vicinity. The detection of black holes has been revolutionized by multi-messenger astronomy, which combines information from different cosmic signals to create a more complete picture of these phenomena. By coordinating observations across the electromagnetic spectrum, as well as gravitational waves and potentially neutrinos, astronomers can study black holes from multiple perspectives simultaneously. This approach was spectacularly demonstrated in 2017, when the neutron star merger GW1 70817 was observed through both gravitational waves and electromagnetic radiation, marking the beginning of a new era in astronomy. While this particular event involved neutron stars rather than black holes, it established the power of multi-messenger techniques that will be applied to future black hole detections. The synergy between different observational methods continues to enhance our ability to detect and study black holes. The development of increasingly sophisticated computer simulations has complemented observational efforts, allowing scientists to model the formation and behavior of black holes in unprecedented detail. These simulations incorporate complex physics, including general relativity, magnetohydrodynamics, and radiation processes, to create virtual black holes, holes that can be compared with real observations. By tweaking parameters in these simulations and comparing the results with observational data, astronomers can test theories about black hole formation, growth, and interaction with their environments. This interplay between simulation and observation has been particularly valuable for understanding processes that occur near the event horizon, where direct observation remains impossible. Each simulation brings us closer to unraveling the mysteries of black hole physics. The detection of black holes has also benefited from advances in statistical methods and machine learning algorithms. With modern telescopes generating enormous amounts of data, traditional manual analysis has become impractical. Machine learning systems can now scan through terabytes of observational data to identify potential black hole candidates based on subtle patterns that might escape human notice. These artificial intelligence systems have proven particularly effective for finding black holes in large surveys, where they can identify promising targets for follow-up observations. The marriage of artificial intelligence with astronomy has accelerated the pace of black hole discoveries, revealing new populations and properties of these cosmic enigmas. Each algorithmic breakthrough expands our ability to detect and understand black holes. The future of black hole detection promises even more exciting developments, with new observatories and techniques currently under development. The Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave detector, will be sensitive to lower frequency gravitational waves than ground-based detectors, allowing it to observe mergers of supermassive black holes. The next generation of extremely large telescopes will provide sharper images of black hole environments, while more sensitive X-ray observatories will detect fainter accretion signatures. These upcoming facilities will undoubtedly reveal new aspects of black hole physics and potentially discover entirely new types of black holes or related phenomena. The continued technological advancement ensures that our ability to detect black holes will keep improving, unveiling more of their secrets. The detection of black holes represents one of the great triumphs of modern astrophysics, transforming these theoretical objects into observable phenomena. Each detection method provides a different piece of the puzzle, contributing to a more complete understanding of black holes and their role in the universe. The techniques developed to detect black holes have also driven innovation in astronomy more broadly, leading to new technologies and approaches that benefit the entire field. The ongoing quest to detect and study black holes continues to push the boundaries of human knowledge, revealing the extreme conditions that exist in the universe and testing our understanding of fundamental physics. Each new detection brings us closer to unraveling the mysteries of these cosmic enigmas. In the cosmic darkness surrounding black holes, there exists a phenomenon of breathtaking beauty and extraordinary power known as accretion disks. These swirling structures of superheated matter form when gas, dust, and other material are drawn toward a black hole by its immense gravitational pull. As this material spirals inward, it forms a flattened, rotating disk that glows with intense radiation, making the invisible black hole visible to our instruments. Accretion disks serve as cosmic lighthouses, illuminating the presence of black holes across vast cosmic distances and allowing us to study these enigmatic objects in remarkable detail. The formation of an accretion disk begins when matter from a companion star or the surrounding interstellar medium is captured by a black hole's gravitational field. This material possesses angular momentum, which prevents it from falling directly into the black hole and instead causes it to orbit in a gradually shrinking spiral. As particles in the disk collide with each other, they lose energy through friction and gravitational interactions, causing them to move to progressively smaller orbits. This process continues until the material eventually crosses the event horizon and disappears from our observable universe, leaving behind only the gravitational signature of its passage. The physics of accretion disks represents one of the most complex and fascinating areas of astrophysical study. Within these disks, matter is subjected to extreme conditions, with temperatures reaching millions of degrees and velocities approaching significant fractions of the speed of light. The intense gravitational forces near a black hole cause the inner regions of the accretion disk to orbit much faster than the outer regions, creating a differential rotation that generates tremendous shear forces. These forces, combined with magnetic fields threading through the disk, drive turbulence and facilitate the transport of angular momentum outward, allowing matter to spiral inward and release gravitational potential energy in the process. The energy released by accretion disks is truly staggering, with some converting gravitational energy into radiation, with efficiencies far greater than nuclear fusion. In fact, accretion onto black holes can be up to 40 times more efficient at converting mass to energy than the nuclear processes that power stars. This extraordinary efficiency makes accretion disks some of the most luminous objects in the universe, capable of outshining entire galaxies despite their relatively small size. The radiation emitted by these disks spans the electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays, providing astronomers with multiple windows through which to observe and study them. One of the most remarkable aspects of accretion disks is their ability to reveal information about the black holes they surround. By analyzing the radiation emitted by these disks, scientists can determine crucial properties of the central black hole, including its mass, spin rate, and even the orientation of its rotation axis. The temperature profile of the disk, for instance, depends on the black hole's mass, with more massive black holes producing cooler disks that emit primarily in ultraviolet and optical wavelengths, while smaller black holes generate hotter disks that glow brightly in X-rays. These observational signatures have allowed astronomers to measure black hole properties with increasing precision, transforming our understanding of these cosmic giants. The structure of accretion disks is not uniform throughout, but exhibits distinct regions with different physical characteristics. The innermost region, located closest to the event horizon, is where the gravitational effects are most extreme and the temperatures reach their peak. This region emits primarily in high-energy X-rays and is where the most interesting physics occurs, including effects predicted by general relativity. Further out, the disk becomes progressively cooler and emits at longer wavelengths, creating a layered structure that can be analyzed to reveal details about the disk's physical conditions. This complex structure provides a rich tapestry of phenomena for astronomers to study and interpret. The appearance of accretion disks is influenced by several factors, including the black hole's spin and the viewing angle from which we observe them. When a black hole rotates, it drags space-time around with it in a phenomenon known as frame dragging, which affects the motion of matter in the inner accretion disk. This effect can cause the disk to precess and create observable variations in the emitted radiation. Additionally, relativistic effects such as beaming and gravitational lensing can distort our view of the disk, making it appear brighter or dimmer depending on our line of sight. These effects, while complicating the analysis of accretion disks, also provide valuable tests of Einstein's theory of general relativity in strong gravitational fields. Accretion disks around stellar mass black holes typically form in binary systems where the black hole is accompanied by a normal star. In these systems, the black hole can strip material from its companion through gravitational attraction, creating a steady stream of gas that feeds the accretion disk. This process can lead to dramatic outbursts when the accretion rate suddenly increases, causing the disk to brighten significantly over a short period. These transient events provide astronomers with opportunities to study accretion physics in detail and have revealed complex behaviors, including state transitions, quasi-periodic oscillations, and jet formation. Each outburst adds to our understanding of how matter behaves under extreme conditions. Supermassive black holes at the centers of galaxies also possess accretion disks, though on vastly larger scales than their stellar mass counterparts. These disks can extend for hundreds or thousands of times the distance from the black hole to its event horizon, encompassing regions where the physics is more familiar and less dominated by relativistic effects. The material feeding these supermassive black holes can come from various sources, including disrupted stars, gas clouds, or even entire galaxies in the process of merging. The accretion disks around supermassive black holes are responsible for some of the most energetic phenomena in the universe, including quasars and active galactic nuclei, which can outshine their host galaxies by factors of thousands or more. The study of accretion disks has revealed that they come in different varieties, each with distinct characteristics and behaviors. Standard thin disks, described by the Shakura-Sunyaev model, are geometrically thin and optically thick, radiating thermally like a blackbody. These disks are well understood and can explain many observed accretion phenomena. In contrast, advection-dominated accretion flows are geometrically thick and optically thin, with much of the heat generated by viscous dissipation being advected inward with the flow rather than radiated away. These different types of accretion flows can coexist in the same system, with transitions between them producing dramatic changes in observable properties. Magnetic fields play a crucial role in the dynamics of accretion disks, influencing their structure, stability, and energy output. These fields can be amplified by the differential rotation of the disk through a process known as the magnetorotational instability, which is thought to be the primary mechanism driving angular momentum transport in accretion disks. The presence of magnetic fields also enables the launching of jets and outflows, which can carry away energy and angular momentum from the disk. These magnetically driven processes are essential for understanding how accretion disks evolve and how they interact with their environments, making them a key area of theoretical and observational research. The radiation emitted by accretion disks provides not only information about the black holes they surround, but also about the physical processes occurring within the disks themselves. By analyzing the spectrum of this radiation, astronomers can determine the temperature distribution, composition, and velocity structure of the disk material. Spectroscopic observations have revealed the presence of various emission and absorption lines that serve as diagnostics for the physical conditions in different regions of the disk. These spectral signatures have been instrumental in confirming theoretical models of accretion physics and in identifying new phenomena that require further theoretical development. Each spectrum tells a story of extreme physical conditions and complex interactions. One of the most intriguing aspects of accretion disks is their variability, with many systems showing fluctuations in brightness on timescales ranging from milliseconds to years. These variations can arise from various physical processes, including instabilities in the disk structure, changes in the accretion rate, or the presence of inhomogeneities orbiting within the disk. The study of this variability has provided insights into the dynamics of accretion disks and has revealed characteristic timescales that can be related to fundamental properties of the black hole. For example, quasi-periodic oscillations observed in X-ray binaries have been used to estimate the masses and spins of stellar mass black holes, demonstrating the power of timing analysis as a diagnostic tool. Accretion disks are not isolated systems, but interact with their environments in complex ways that can influence both the disks themselves and their surroundings. Outflows and winds launched from accretion disks can inject energy and momentum into the surrounding medium, potentially regulating further accretion and affecting the evolution of the host system. Jets, which are highly collimated beams of particles moving at nearly the speed of light, can extend for thousands of light years and interact with the intergalactic medium, creating large-scale structures visible across cosmic distances. These interactions demonstrate that accretion disks are not merely passive structures, but active agents that shape their environments and contribute to the evolution of cosmic structures. The study of accretion disks has benefited greatly from advances in computational modeling, which allows scientists to simulate the complex physics of these systems in unprecedented detail. Modern simulations incorporate general relativity, magnetohydrodynamics, and radiation transport to create virtual accretion disks that can be compared with observational data. These simulations have revealed intricate details about disk structure, stability, and evolution that would be impossible to observe directly. They have also helped researchers understand how accretion disks form in the first place and how they respond to changes in the supply of accreting material. Each computational breakthrough brings us closer to a complete understanding of accretion physics. Accretion disks serve as natural laboratories for studying physics under extreme conditions that cannot be replicated on Earth. The intense gravitational fields, high temperatures, and rapid velocities found in these disks test the limits of our current physical theories and provide opportunities to discover new phenomena. For example, the study of accretion disks has led to insights into plasma physics, fluid dynamics, and radiative processes that have applications beyond astrophysics. The knowledge gained from studying these cosmic lighthouses contributes to our broader understanding of the physical world and drives innovation in both theoretical and experimental physics. Each discovery in accretion disk research has ripple effects throughout the scientific community. The formation and evolution of accretion disks are closely tied to the life cycles of black holes and their host systems. In the early universe, accretion onto the first supermassive black holes may have played a crucial role in reionizing the intergalactic medium and shaping the formation of early galaxies. Throughout cosmic history, accretion disks have been engines of cosmic evolution, converting gravitational energy into radiation that influences star formation and galactic development. Even today, accretion disks continue to drive the evolution of galaxies and the growth of black holes, maintaining a delicate balance between gravitational collapse and energetic feedback. Understanding these processes is essential for reconstructing the history of the universe and predicting its future evolution. The observational study of accretion disks has been revolutionized by new technologies and facilities that allow astronomers to probe these systems with ever-increasing sensitivity and resolution. Space-based X-ray telescopes like Chandra and XMM Newton have provided detailed views of the high-energy regions close to black holes, while radio interferometers such as the Event Horizon Telescope have achieved resolutions sufficient to image the shadow of a black hole against its accretion disk. These technological advances have transformed accretion disks from theoretical constructs into observable phenomena with measurable properties. Each new observational capability reveals new aspects of accretion disk physics and raises new questions for future research. As we continue to study accretion disks, we find that they are even more complex and fascinating than initially imagined. Recent observations have revealed unexpected phenomena, such as disk winds with complex geometries, quasi-periodic eruptions in active galactic nuclei, and evidence for magnetically arrested disks around rapidly spinning black holes. These discoveries challenge our current understanding and drive the development of new theoretical models. The study of accretion disks remains a vibrant field of research, with each new observation bringing fresh insights into the physics of these cosmic lighthouses and the black holes they illuminate. The ongoing exploration of accretion disks promises to reveal even deeper mysteries about the nature of spacetime and the behavior of matter under extreme conditions. The beauty of accretion disks lies not only in their visual splendor, but also in the profound physics they embody. These swirling structures of superheated matter represent the cosmic dance between gravity and thermodynamics, between order and chaos, between destruction and creation. They are places where matter is transformed into energy with extraordinary efficiency, where the laws of physics are tested at their limits, and where the invisible becomes visible through the power of gravitational attraction. In studying accretion disks, we are not just learning about black holes, but about the fundamental processes that govern the evolution of the universe. Each discovery in this field brings us closer to understanding our place in the cosmic tapestry and the elegant simplicity of the physical laws that shape our reality. In the cosmic dance of matter and energy around black holes, there exists a phenomenon of extraordinary power and beauty that extends far beyond the immediate vicinity of these enigmatic objects. Jets and outflows are among the most spectacular manifestations of black hole activity, launching material at nearly the speed of light across vast cosmic distances. These highly collimated beams of particles and energy emerge from the regions near black holes, piercing through the surrounding space and influencing environments thousands of light years away. The study of these cosmic fountains has revealed that black holes are not merely passive consumers of matter, but active agents that profoundly shape their surroundings through these energetic outflows. The formation of jets near black holes represents one of the most fascinating puzzles in modern astrophysics. These narrow streams of plasma can extend for hundreds of thousands of light years, yet they originate from regions smaller than our solar system. The exact mechanisms that launch and collimate these jets are still not fully understood, though most theories involve a combination of the black hole's rotation, magnetic fields, and the accretion process. As matter spirals inward in the accretion disk, it interacts with magnetic fields that are twisted by the black hole's rotation, launching material along the polar axes where resistance is minimal. This process converts gravitational energy into kinetic energy with remarkable efficiency, creating some of the most energetic phenomena in the universe. Jets come in different varieties, each associated with different types of black holes and accretion processes. Stellar mass black holes in binary systems typically produce smaller, shorter-lived jets that can be observed over timescales of days to months. In contrast, supermassive black holes at the centers of galaxies can generate enormous jets that persist for millions of years and extend far beyond their host galaxies into the intergalactic medium. These relativistic jets are among the most persistent and large-scale structures in the universe, serving as cosmic signposts that reveal the presence of supermassive black holes across cosmic time. The diversity of jet properties reflects the complex physics governing their formation and evolution. One of the most remarkable aspects of astrophysical jets is their ability to maintain tight collimation over enormous distances. Unlike a simple explosion that would spread out in all directions, these jets remain focused in narrow beams that can travel across multiple galaxies without significant dispersion. This collimation is thought to be maintained by magnetic fields that guide the flow and confine it to a narrow channel. The stability of these magnetic structures over such vast distances and timescales represents a significant challenge to theoretical models, requiring sophisticated magneto-hydrodynamic simulations to understand the underlying physics. Each jet observed provides valuable data for testing these models and refining our understanding of plasma behavior under extreme conditions. The interaction between jets and their surroundings creates some of the most spectacular structures visible in the universe. When these high-speed outflows encounter the intergalactic medium, they create enormous cavities and shockwaves that heat the surrounding gas and influence star formation. These interactions can be observed in X-ray and radio wavelengths, revealing bubbles of relativistic plasma surrounded by shells of compressed material. The largest known examples of these structures, called radiolobes, can span millions of light years and contain enough energy to power 100 billion stars. These cosmic sculptures stand as monuments to the profound influence that black holes can exert on their environments, long after the initial jet activity has ceased. Jets also play a crucial role in regulating the growth of galaxies and their central black holes through a process known as feedback. The energy injected by jets into the surrounding medium can heat gas that would otherwise cool and collapse to form new stars, effectively shutting down star formation in the host galaxy. This feedback mechanism creates a delicate balance between the growth of the black hole and the evolution of its host galaxy, explaining observed correlations between black hole mass and galaxy properties. Without this regulatory process, galaxies might evolve very differently, potentially becoming much larger or forming stars at different rates than we observe. The feedback loop represents one of the most important connections between black holes and large-scale cosmic structure. The study of jets has revealed that they are not steady, continuous flows, but exhibit complex variability on multiple timescales. Some jets show dramatic flaring activity, brightening by orders of magnitude over periods of days or weeks before returning to quiescence. Others display more subtle variations that reveal details about the physical processes occurring near the black hole. This variability can arise from changes in the accretion rate, instabilities in the jet formation region, or interactions with obstacles in the jet path. By analyzing these variations, astronomers can probe conditions in regions too small to resolve directly, effectively using the jet itself as a probe of the black hole environment. Each fluctuation tells a story of dynamic processes occurring in these extreme cosmic laboratories. Jets also serve as cosmic accelerators, boosting particles to energies far beyond what can be achieved in human-made particle accelerators. The exact mechanisms responsible for this particle acceleration are still debated, but likely involve shockwaves within the jet and magnetic reconnection events. These accelerated particles, which can include electrons, protons, and possibly atomic nuclei, radiate across the electromagnetic spectrum through synchrotron and inverse Compton processes. The highest energy particles may even escape into the intergalactic medium, contributing to the population of cosmic rays that bombard Earth. Understanding these acceleration processes has implications not only for astrophysics, but also for plasma physics and high-energy particle theory. The polarization of radiation from jets provides valuable information about the magnetic fields that thread through them. By measuring how much the light from a jet is polarized and in what direction, astronomers can infer the strength and geometry of the magnetic fields responsible for launching and collimating the jet. These observations have revealed that magnetic fields play a crucial role in jet dynamics, with field lines that are initially toroidal, circling the jet axis, gradually becoming more longitudinal, parallel to the jet direction, at greater distances. This evolution of magnetic field structure provides important constraints for theoretical models of jet formation and propagation. Each polarization measurement adds another piece to the puzzle of how these remarkable structures form and maintain themselves. Jets are not the only type of outflow associated with black holes. Slower, wider-angle winds are also commonly observed. These winds, which can be driven by radiation pressure, magnetic forces, or thermal pressure, carry mass and energy away from the accretion disk at sub-relativistic speeds. Unlike highly collimated jets, these winds expand in broader cones and can interact with the surrounding medium in different ways. The study of these outflows has revealed that they can carry away a significant fraction of the material that would otherwise accrete onto the black hole, effectively regulating its growth rate. The coexistence of jets and winds suggests that black holes can influence their surroundings through multiple channels, each with distinct characteristics and effects. The interaction between jets and the interstellar medium of their host galaxies creates complex feedback loops that influence galaxy evolution. When jets plow into the dense gas within a galaxy, they can compress clouds of gas in some regions while dispersing it in others, creating a patchwork of stimulated and suppressed star formation. This feedback can be both positive and negative, with some areas experiencing enhanced star formation due to jet-induced compression, while others see star formation quenched by heating and gas removal. The net effect depends on various factors, including the jet power, the density distribution of the gas, and the orientation of the jet relative to the galaxy. Understanding these feedback processes is essential for modeling how galaxies evolve over cosmic time. Jets also serve as signposts for some of the most energetic events in the universe, including gamma-ray bursts and active galactic nuclei. When jets are pointed directly toward Earth, they appear as blazars, among the brightest and most variable objects in the sky. These systems can exhibit dramatic flares across the electromagnetic spectrum, from radio waves to gamma rays, providing natural laboratories for studying particle acceleration and radiation processes under extreme conditions. The study of these aligned jets has revealed that they can accelerate particles to energies exceeding those achieved in the Large Hadron Collider, making them invaluable probes of high-energy physics. Each observation of a blazar outburst offers new insights into the physics of relativistic jets and the extreme environments near black holes. The formation of jets is intimately connected to the spin of the black hole, according to theoretical models. Rapidly rotating black holes can extract rotational energy through magnetic fields that thread the event horizon, a process known as the Blandford-Znaiec mechanism. This energy extraction can power jets more efficiently than accretion alone, potentially explaining why some black holes produce much more powerful jets than others. The spin of a black hole thus becomes a crucial parameter in determining its jet-producing capability, creating a direct link between the black hole and the jet hole's intrinsic properties and its observable effects on the surrounding environment. Measuring black hole spins through jet observations has become an important tool in understanding the population properties of these cosmic giants. Jets also play a role in the cosmic ecosystem by transporting metals and other heavy elements far from their sites of origin. As jets propagate through galaxies and into the intergalactic medium, they entrain material that has been enriched by stellar evolution, distributing these elements across vast cosmic distances. This process contributes to the chemical evolution of the universe, seeding regions that might otherwise remain pristine with the building blocks for planets and life. The redistribution of elements by jets represents yet another way in which black holes influence cosmic evolution, connecting the smallest scales of stellar nucleosynthesis to the largest structures in the universe. Each jet that carries enriched material contributes to the ongoing chemical evolution of the cosmos. The study of jets has been revolutionized by multi-wavelength observations that capture different aspects of these complex phenomena. Radio telescopes reveal the structure and magnetic fields of jets. X-ray observatories probe the highest energy regions near the black hole, and optical telescopes track the motion of material in jet components. By combining these different views, astronomers can construct a more complete picture of jet physics than would be possible with any single wavelength. This multi-wavelength approach has been particularly valuable for understanding the connection between accretion processes and jet formation, revealing correlations that provide clues about the underlying physical mechanisms. Each new observational window adds depth to our understanding of these cosmic phenomena. Jets also serve as probes of the intervening space between their source and Earth, providing information about the distribution of matter and magnetic fields in the universe. As jet radiation travels through space, it can be absorbed, scattered, or polarized by intervening material, leaving imprints that reveal the properties of these regions. This effect has been used to study the magnetic fields within galaxies and the intergalactic medium, as well as to detect otherwise invisible clouds of gas along the line of sight. In this way, jets become not just objects of study in themselves, but also tools for investigating the cosmic environment through which they propagate. Each jet observed carries information about multiple regions of space, from near the black hole to Earth. Theoretical models of jet formation have evolved significantly over the past few decades, incorporating increasingly sophisticated physics to explain these remarkable phenomena. Early models focused on hydrodynamic processes, but modern approaches recognize the essential role of magnetic fields in launching and collimating jets. General relativistic magnetohydrodynamic simulations can now model the complex interplay between gravity, magnetic fields, and plasma dynamics in the vicinity of black holes, providing detailed predictions that can be compared with observations. These simulations have revealed that jet formation is a robust process that can occur under a wide range of conditions, explaining why jets are observed around both stellar mass and supermassive black holes. Each computational advance brings us closer to a complete theoretical understanding of jet physics. Jets also play a crucial role in the co-evolution of black holes and their host galaxies over cosmic time. By regulating both the growth of the black hole through feedback and the star formation rate in the galaxy, jets help establish the observed correlations between black hole mass and galaxy properties. This co-evolutionary relationship suggests that jets are not merely byproducts of accretion, but essential components in the cosmic ecosystem that connects black holes to their environments. Understanding this relationship has become a central goal in modern astrophysics, with implications for our understanding of galaxy formation and evolution throughout cosmic history. The study of jets thus connects the physics of black holes to the largest structures in the universe. The variability of jets on human timescales provides a unique opportunity to study processes that occur near the event horizon. Unlike many astronomical phenomena that evolve over millions of years, jets can show detectable changes over periods of days or weeks, allowing astronomers to watch the dynamics unfold in real time. This variability has been used to measure the size of the emitting regions, track the motion of jet components, and identify the mechanisms responsible for flaring activity. In some cases, these observations have revealed superluminal motion, where jet components appear to move faster than light due to relativistic effects beamed toward Earth. Each variability study adds to our understanding of the physical processes occurring in these extreme environments. Jets also have implications for the study of dark matter and the large-scale structure of the universe. By heating and redistributing gas in galaxy clusters, jets can influence the distribution of both visible and dark matter, potentially affecting the formation of cosmic structures. This connection between small-scale processes near black holes and the large-scale structure of the universe represents one of the most fascinating aspects of modern astrophysics. It suggests that understanding jets is essential not only for black hole physics, but also for cosmology and the evolution of the universe as a whole. The study of these cosmic outflows thus bridges multiple scales and disciplines in astrophysics. As we continue to study jets and outflows from black holes, we find that they are even more complex and influential than initially imagined. Recent observations have revealed jets with unexpected structures, including helical patterns, knots, and bends that suggest complex interactions with their environments. Other studies have found evidence for jet precession, where the direction of the jet changes over time, creating intricate patterns in the surrounding medium. These discoveries challenge our current understanding and drive the development of new theoretical models to explain these phenomena. The ongoing exploration of jets promises to reveal even deeper mysteries about the nature of black holes and their role in shaping the cosmos. The beauty of jets lies not only in their spectacular appearance, but also in the profound physics they embody. These cosmic fountains represent the conversion of gravitational energy into kinetic energy with extraordinary efficiency, creating structures that persist for millions of years and influence environments across vast cosmic distances. They are places where magnetic fields, plasma dynamics, and relativistic effects combine to create phenomena that challenge our understanding and inspire our imagination. In studying jets, we are not just learning about black holes, but about the fundamental processes that govern the behavior of matter and energy under extreme conditions. Each discovery in this field brings us closer to understanding our place in the cosmic tapestry and the elegant simplicity of the physical laws that shape our reality. In the vast expanse of cosmic exploration, few achievements have captured the imagination quite like the first direct image of a black hole's shadow. This monumental accomplishment, announced in April 2019 by the Event Horizon Telescope collaboration, marked a pivotal moment in our understanding of these enigmatic cosmic entities. For decades, black holes remained theoretical constructs, their presence inferred only through their gravitational influence on surrounding matter and light. The quest to directly observe these mysterious objects represented one of the greatest challenges in astronomy, requiring unprecedented technological innovation and international cooperation. The successful imaging of a black hole's shadow not only confirmed Einstein's predictions, but also opened a new window into the study of these cosmic giants. The challenge of capturing an image of a black hole stems from the very nature of these objects. By definition, black holes do not emit light, making them invisible against the darkness of space. Their presence can only be detected through the effects they exert on their surroundings, such as the gravitational lensing of light from background sources, or the radiation emitted by matter as it spirals inward. To directly observe a black hole, astronomers needed to target the event horizon, the boundary beyond which nothing can escape, including light itself. This region appears as a dark silhouette against the brighter backdrop of superheated matter swirling around the black hole, creating what scientists refer to as the black hole's shadow. Capturing this shadow required resolving details smaller than any previously achieved in astronomical imaging. The Event Horizon Telescope project represented an ambitious solution to this formidable challenge. Rather than building a single enormous telescope, which would be practically impossible, the collaboration linked together radio telescopes across the globe to create a virtual Earth-sized telescope. This technique, known as very long baseline interferometry, effectively created a telescope with the resolving power of a dish the size of our planet. The project involved 8 radio observatories, strategically positioned around the world, from Hawaii to Europe, from the Americas to Antarctica. By combining the data from these telescopes, astronomers could achieve the angular resolution necessary to resolve the event horizon of a supermassive black hole, despite its distance of millions of light years. The technical challenges faced by the Event Horizon Telescope team were immense. Each telescope in the network had to be equipped with highly sensitive atomic clocks to precisely timestamp the incoming radio waves, allowing the data to be properly synchronized when combined later. The telescopes observed simultaneously for several days in April 2017, targeting 2 supermassive black holes, Sagittarius, a star at the center of our Milky Way galaxy, and the black hole in the galaxy M87, located about 55 million light-years away. The weather had to be clear at all sites during the observation period, a requirement that was particularly challenging for the South Pole Telescope, which had to operate during the Antarctic winter. The amount of data collected was so enormous that it had to be physically transported on hard drives rather than transmitted over the internet. The data processing phase presented its own set of formidable challenges. The combined data from the global telescope network contained about 5 petabytes of information, equivalent to thousands of hours of high-definition video. This data had to be meticulously processed using specialized algorithms to reconstruct an image from the interference patterns created by radio waves arriving at different telescopes. The processing was complicated by the fact that the Earth's rotation continuously changed the relative positions of the telescopes, creating a constantly evolving interferometric pattern. To ensure the reliability of the final image, the research team developed multiple independent imaging techniques and compared their results, a process that took nearly 2 years to complete. The announcement of the first image of a black hole's shadow on April 10th, 2019, captivated the world and marked a historic milestone in astronomy. The image revealed a dark, circular region, surrounded by a bright ring of emission, precisely matching theoretical predictions of what a black hole's shadow should look like. This particular black hole resides at the center of the galaxy M87 and has a mass approximately 6.5 billion times that of our Sun. The image confirmed that the dark region at the center was indeed the shadow of the event horizon, while the bright ring was produced by radiation from superheated matter swirling around the black hole at nearly the speed of light. This visual confirmation provided compelling evidence for the existence of black holes and validated Einstein's theory of general relativity in the strong field regime. The significance of this achievement extends far beyond simply obtaining a striking image. For the first time, astronomers could directly observe the effects of extreme gravity on the propagation of light, testing general relativity in ways previously impossible. The size and shape of the black hole's shadow provided precise measurements of the black hole's mass and spin, parameters that are crucial for understanding how these objects form and evolve. The image also revealed details about the accretion flow and jet formation near the event horizon, shedding light on the complex physics of how black holes interact with their surroundings. Each piece of information extracted from this image has contributed to our understanding of black hole physics and the behavior of matter under extreme conditions. The technology developed for the Event Horizon Telescope project has opened new frontiers in astronomical observation. By demonstrating the feasibility of very long baseline interferometry at millimeter wavelengths, the project has paved the way for even more ambitious observations in the future. The techniques developed for data processing and image reconstruction have applications beyond black hole imaging, potentially improving our ability to study other astronomical phenomena with unprecedented resolution. The success of the project also showcased the power of international scientific collaboration, bringing together researchers from around the world to achieve a common goal. This model of cooperation may serve as a template for future large-scale scientific endeavors. The image of the M87 black hole's shadow has also had a profound impact on public engagement with science. The striking visual representation of a phenomenon that had previously existed only in equations and simulations captured the public imagination in a way that technical descriptions rarely achieve. The image was widely shared across media platforms and became a cultural touchstone, symbolizing human curiosity and our capacity to understand the universe. This public engagement has helped to communicate the importance of fundamental research and has inspired a new generation of students to pursue careers in science, technology, engineering, and mathematics. The cultural impact of this achievement demonstrates how scientific discoveries can resonate beyond the academic community. The Event Horizon Telescope collaboration has continued to improve its capabilities since the 2019 announcement. Additional telescopes have been added to the network, enhancing the coverage and sensitivity of the array. New observations have been conducted, including further studies of both the M87 black hole and Sagittarius A star at the center of our galaxy. The analysis techniques have been refined, allowing for more detailed extraction of physical parameters from the data. These ongoing efforts are gradually building a more comprehensive picture of black hole physics and the extreme environments near event horizons. Each improvement brings us closer to understanding the fundamental nature of these cosmic enigmas. One of the most exciting prospects for the future of black hole imaging is the potential to create movies of black hole dynamics rather than static images. By observing how the shadow and surrounding emission change over time, astronomers could study the dynamic processes near the event horizon, including the behavior of magnetic fields and the formation of jets. This would require sustained observations over extended periods, presenting additional technical challenges, but offering the potential for unprecedented insights into black hole physics. The Event Horizon Telescope team is already working toward this goal, with plans for more frequent observations and improved data processing techniques that can capture temporal variations in the black hole's appearance. The study of black hole shadows also provides a unique opportunity to test alternative theories of gravity. While Einstein's general relativity has passed all tests so far, there are reasons to believe that it may not be the final word on gravity, particularly in the extreme conditions near black hole event horizons. Some alternative theories predict subtle differences in the size and shape of black hole shadows compared to general relativity. By making increasingly precise measurements of these shadows, astronomers can place constraints on alternative theories and potentially discover new physics. This represents a new frontier in the experimental testing of gravitational theories, complementing other approaches such as gravitational wave detection. The imaging of black hole shadows has also stimulated theoretical work to better understand what these images can tell us about the underlying physics. Sophisticated computer simulations now model the appearance of black holes under various conditions, incorporating general relativity, magnetohydrodynamics, and radiation transport. These simulations can be compared directly with observational data to test our understanding of the physical processes near event horizons. The interplay between theory and observation has already led to new insights into accretion physics, jet formation, and the behavior of magnetic fields in these extreme environments. Each theoretical advance helps to interpret the observational data more effectively, creating a virtuous cycle of discovery. The Event Horizon Telescope project has also inspired the development of next-generation observatories that will further enhance our ability to study black holes. Plans are underway for the next-generation Event Horizon Telescope, which will include additional telescopes, observe at multiple frequencies, and employ advanced signal processing techniques. These improvements will allow for sharper images with greater detail, potentially revealing finer structures near the event horizon. There are also proposals for space-based, very long baseline interferometry, which could create a virtual telescope larger than Earth and achieve even higher resolution. These future developments promise to build on the success of the initial black hole imaging and open new avenues for exploration. The first image of a black hole's shadow represents more than just a technological achievement. It symbolizes the culmination of a century-long journey to understand one of the most mysterious phenomena in the universe. From Einstein's theoretical prediction of black holes in 1915 to the first direct observation in 2019, this journey has involved countless scientists, engineers, and support staff working together to push the boundaries of human knowledge. The image stands as a testament to human curiosity and our capacity to unravel the mysteries of the cosmos through persistent inquiry and technological innovation. It reminds us that even the most elusive phenomena in the universe can eventually yield to the combined efforts of determined researchers. The cultural impact of the black hole image extends beyond its scientific significance. influencing art, literature, and popular culture. The distinctive appearance of the dark circle, surrounded by a bright ring, has become an iconic representation of black holes in visual media. This cultural resonance reflects the deep fascination that black holes hold for the human imagination, representing the unknown and the seemingly impossible. The image has served as a bridge between the technical world of astrophysics and public understanding, making abstract concepts tangible and accessible. This cultural impact helps to maintain public support for scientific research and inspires continued exploration of the cosmos. As we reflect on the achievement of capturing the first image of a black hole's shadow, we are reminded of how far our understanding of the universe has progressed. What was once considered purely theoretical and perhaps unobservable has now been directly imaged and studied in detail. This milestone represents not an endpoint, but rather a beginning, opening new questions and avenues for research. The study of black holes continues to evolve, with each discovery raising new puzzles and challenges. The first image of a black hole's shadow has provided a foundation upon which future research can build, promising even deeper insights into these cosmic enigmas in the years to come. The techniques developed for black hole imaging have applications beyond astronomy, particularly in the field of computational imaging. The algorithms created to reconstruct images from sparse interferometric data can be adapted for medical imaging, remote sensing, and other fields where high-resolution imaging is challenging. This cross-pollination of ideas between astronomy and other disciplines demonstrates how fundamental research often leads to unexpected technological innovations with broad societal benefits. The Event Horizon Telescope project thus serves as an example of how curiosity-driven scientific exploration can yield practical applications that improve our lives in ways not anticipated at the outset of the research. Looking to the future, the study of black hole shadows promises to reveal even more about these cosmic mysteries. With improved instrumentation and analysis techniques, astronomers hope to detect subtle features in the shadow that could provide information about the black hole's spin, the orientation of its accretion disk, and the physics of the event horizon itself. There is also the possibility of detecting the effects of quantum gravity, which might manifest as small deviations from the predictions of classical general relativity. These future observations could potentially revolutionize our understanding of gravity and spacetime, bridging the gap between general relativity and quantum mechanics. Each new observation brings us closer to unraveling the deepest mysteries of the universe. The journey to capture the first image of a black hole's shadow also highlights the importance of long-term investment in fundamental research. The Event Horizon Telescope project was decades in the making, requiring sustained support from funding agencies and institutions. This long-term perspective is essential for tackling the most challenging questions in science, which often cannot be answered through short-term projects. The success of this endeavor demonstrates the value of patient investment in curiosity-driven research and the remarkable returns that such investments can yield, both in terms of scientific knowledge and technological innovation. It serves as a reminder that some of the most profound discoveries require time, persistence, and unwavering support. As we contemplate the significance of the first image of a black hole's shadow, we are reminded of the profound connection between theoretical prediction and observational confirmation in science. Einstein's theory of general relativity, developed more than a century ago, predicted the existence of black holes and described how they would bend light and cast shadows. The 2019 image provided a stunning visual confirmation of these predictions, validating one of the most successful theories in the history of physics. This interplay between theory and observation lies at the heart of the scientific method, driving our understanding of the universe forward through a continuous process of prediction, testing, and refinement. The image of the M87 black hole's shadow has also stimulated public interest in the fundamental questions of physics and cosmology. People around the world have been inspired to learn more about black holes, gravity, and the nature of spacetime. This public engagement has created opportunities for science education and outreach, helping to communicate complex concepts in accessible ways. The image has become a powerful tool for educators, providing a concrete example that can be used to illustrate abstract ideas about gravity, light, and the behavior of matter under extreme conditions. This educational impact ensures that the next generation will be well informed about the wonders of the universe and the methods of scientific inquiry. The success of the Event Horizon Telescope project has also strengthened international cooperation in science. The collaboration involved researchers from institutions across the globe, working together to achieve a common goal that transcended national boundaries. This model of international scientific cooperation serves as an example of how humanity can come together to tackle grand challenges, regardless of political or cultural differences. The project demonstrated that the pursuit of knowledge can be a unifying force, bringing people together in a shared endeavor that benefits all of humanity. This spirit of cooperation will be essential as we face the increasingly complex challenges of the 21st century. As we continue to study black holes and their shadows, we are reminded of the vastness of the universe and the mysteries that still await discovery. The first image of a black hole's shadow represents not an end, but a beginning, opening new questions and avenues for exploration. Each discovery in this field leads to new puzzles, driving the cycle of scientific inquiry forward. The study of black holes connects the smallest scales of quantum physics to the largest structures in the universe, revealing deep connections between seemingly disparate phenomena. In this way, the exploration of black holes serves as a microcosm of the scientific endeavor itself, a journey into the unknown that continually expands our understanding of reality. In the vast cosmic tapestry of galaxies, there exist mysterious entities of immense power and influence that reside at the very heart of these stellar archipelagos. These cosmic giants, known as supermassive black holes, contain masses equivalent to millions or even billions of times that of our Sun, compressed into regions smaller than our solar system. Their discovery has revolutionized our understanding of galaxy formation and evolution, revealing a profound connection between these dark behemoths and the visible structures they inhabit. The presence of supermassive black holes at galactic centers represents one of the most significant findings in modern astronomy, transforming our perception of how galaxies are born, evolve, and ultimately shape the cosmic landscape. The journey to uncover these galactic hearts began with observations of unusual activity in the centers of some galaxies, which appeared unusually bright and energetic compared to their outer regions. Astronomers noted that these galactic nuclei emitted tremendous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, suggesting the presence of extremely energetic processes occurring within compact regions. The behavior of stars near the centers of galaxies provided additional clues, with some stars moving at incredible speeds, indicating the presence of a massive, unseen object exerting powerful gravitational forces. These observations gradually built a compelling case for the existence of supermassive black holes lurking at the cores of galaxies, including our own Milky Way. Our own galaxy, the Milky Way, harbors a supermassive black hole named Sagittarius, a star, located approximately 26,000 light-years from Earth, in the direction of the constellation Sagittarius. This cosmic giant, with a mass about 4 million times that of our Sun, influences the orbits of nearby stars, causing them to move in elliptical paths at speeds reaching thousands of kilometers per second. The careful tracking of these stellar orbits over decades has provided some of the most compelling evidence for the existence of supermassive black holes, allowing astronomers to precisely measure the mass and location of Sagittarius A star with remarkable accuracy. The study of our galactic center has served as a crucial laboratory for understanding the physics of supermassive black holes and their interactions with their environments. Supermassive black holes are not rare anomalies, but common features of galaxies throughout the universe, with observations suggesting that nearly all large galaxies contain one at their center. The mass of these central black holes exhibits a surprising correlation with various properties of their host galaxies, including the mass of the galactic bulge, the velocity dispersion of stars, and the total luminosity of the galaxy. These relationships, known as scaling relations, imply a deep connection between the growth of supermassive black holes and the evolution of their host galaxies, suggesting that they co-evolve over cosmic time. The existence of such correlations across galaxies of different sizes and types points to fundamental physical processes that regulate the growth of both black holes and galaxies. The formation of supermassive black holes presents a significant challenge to our understanding of the early universe, as these objects must have accumulated their enormous masses relatively quickly after the Big Bang. Several theories have been proposed to explain their origins, including the collapse of massive primordial gas clouds, the merger of smaller black holes, and the direct collapse of extremely massive stars in the early universe. Each of these mechanisms presents different challenges and predictions, and it is likely that multiple processes contributed to the formation and growth of supermassive black holes throughout cosmic history. The study of distant quasars, which are powered by accretion onto supermassive black holes, has revealed that these objects existed when the universe was less than 1 billion years old, providing crucial constraints on theories of their formation. The influence of supermassive black holes extends far beyond their immediate vicinity, shaping the structure and evolution of their host galaxies through various feedback mechanisms. As matter falls toward a supermassive black hole, it forms an accretion disk that heats to extreme temperatures and emits enormous amounts of radiation, which can heat and ionize gas throughout the galaxy. Additionally, many supermassive black holes produce powerful jets and outflows that inject energy and momentum into the surrounding medium, potentially regulating star formation and influencing the distribution of matter within the galaxy. These feedback processes create a delicate balance between the growth of the black hole and the evolution of its host galaxy, establishing the observed correlations between black hole mass and galaxy properties. The energy output from accretion onto supermassive black holes can be truly staggering, with some active galactic nuclei outshining their entire host galaxies by factors of hundreds or thousands. These luminous objects, known as quasars, blazars, and Seyfert galaxies, depending on their specific properties, represent some of the most energetic phenomena in the universe. The study of these active galactic nuclei has revealed that they are powered by the conversion of gravitational potential energy into radiation as matter spirals inward toward the event horizon, with efficiencies far exceeding those of nuclear fusion processes. By analyzing the radiation from these objects, astronomers can probe the physical conditions near supermassive black holes and study the properties of these cosmic engines across cosmic time. The growth of supermassive black holes over cosmic history represents a complex interplay between accretion, mergers, and feedback processes. Supermassive black holes can grow by accreting gas and dust from their surroundings, as well as by merging with other black holes when galaxies collide. These growth processes are regulated by feedback mechanisms that can either fuel or suppress further accretion, depending on the specific conditions. The cosmic evolution of supermassive black holes is closely tied to the evolution of galaxies themselves, with periods of rapid black hole growth often coinciding with periods of intense star formation and galaxy assembly. Understanding this co-evolutionary process remains one of the central goals of modern astrophysics. The detection of supermassive black holes in the early universe has profound implications for our understanding of cosmic evolution. Observations have revealed quasars powered by supermassive black holes with masses exceeding 1 billion times that of our Sun, when the universe was less than 1 billion years old. These distant objects challenge our models of black hole formation and growth, as they must have accumulated their enormous masses in a relatively short cosmic time frame. The existence of such massive black holes in the early universe suggests that the conditions for their formation were different from those in the local universe, potentially involving direct collapse of massive gas clouds or unusually efficient accretion processes. These findings continue to drive theoretical efforts to understand the origins of supermassive black holes and their role in shaping the early universe. The relationship between supermassive black holes and their host galaxies extends to the largest scales of cosmic structure, influencing the formation and evolution of galaxy clusters and superclusters. The energy injected by supermassive black holes can heat the intracluster medium, preventing excessive cooling and star formation in the central regions of galaxy clusters. This feedback process helps explain why the most massive galaxies in clusters are often relatively quiescent, with lower rates of star formation than would be expected based on their gas content. The influence of supermassive black holes thus extends from the scales of individual galaxies to the largest structures in the universe, demonstrating their profound impact on cosmic evolution. The study of supermassive black holes has been revolutionized by advances in observational technology, particularly in the realms of X-ray astronomy, radio interferometry, and more recently, gravitational wave detection. Space-based X-ray telescopes like Chandra and XMM Newton have provided detailed views of the high-energy processes occurring near supermassive black holes, while radio interferometers such as the Event Horizon Telescope have achieved resolutions sufficient to image the immediate vicinity of these objects. The recent detection of gravitational waves from merging black holes has opened an entirely new window on the universe, allowing us to observe the coalescence of black holes in ways previously impossible. These technological advances continue to transform our understanding of supermassive black holes and their role in the cosmos. The properties of supermassive black holes vary widely across the population, with masses ranging from millions to billions of solar masses and accretion rates spanning orders of magnitude. This diversity reflects the different evolutionary histories of their host galaxies and the varying conditions under which these black holes have grown. Some supermassive black holes are actively accreting matter and producing intense radiation, while others are relatively quiescent, with little current accretion activity. Understanding this diversity and its relationship to galaxy properties remains an active area of research, with implications for our understanding of galaxy evolution and the life cycles of supermassive black holes. Each new observation adds to our knowledge of these cosmic giants and their place in the universe. The influence of supermassive black holes on star formation in their host galaxies represents a crucial aspect of their role in cosmic evolution. Through various feedback mechanisms, supermassive black holes can either stimulate or suppress star formation, depending on the specific conditions and the nature of the feedback. Positive feedback can occur when jets or outflows compress gas clouds, triggering gravitational collapse and subsequent star formation. Negative feedback, on the other hand, occurs when the energy injected by the black hole heats gas and prevents it from cooling and collapsing to form stars. The balance between these processes helps determine the star formation history of a galaxy and contributes to the observed correlations between black hole mass and galaxy properties. The study of supermassive black holes has revealed unexpected connections between these cosmic giants and seemingly unrelated phenomena in the universe. For example, the spin of a supermassive black hole can influence the power and direction of its jets, which in turn can affect the distribution of heavy elements throughout the galaxy and beyond. The magnetic fields generated by accretion disks around supermassive black holes play a crucial role in jet formation and collimation, connecting the behavior of these fields to large-scale galactic outflows. These complex interrelationships highlight the intricate web of physical processes that connect supermassive black holes to their environments and demonstrate the profound influence these objects exert on cosmic evolution. As we continue to study supermassive black holes, we find that they are even more complex and influential than initially imagined. Recent observations have revealed that supermassive black holes can be displaced from the exact centers of their host galaxies, potentially due to gravitational interactions with other massive objects or the recoil from asymmetric gravitational wave emission during mergers. Other studies have found evidence for binary supermassive black holes, which are expected to form when galaxies merge and their central black holes eventually coalesce. These discoveries challenge our understanding of black hole dynamics and galaxy evolution, suggesting that the relationship between supermassive black holes and their host galaxies is more complex than previously thought. Each new finding adds depth to our understanding of these cosmic giants and their role in shaping the universe. In the grand cosmic narrative, few relationships are as intricate and profound as that between black holes and their host galaxies, a connection that has unfolded over billions of years. This cosmic dance, characterized by mutual growth and influence, has shaped the universe we observe today, creating the diverse population of galaxies and their central black holes. The discovery of correlations between black hole mass and various galaxy properties has revealed that these objects do not evolve independently, but rather as interconnected components of a larger system. Understanding this co-evolutionary process has become one of the central pursuits in modern astrophysics, offering insights into the formation and development of cosmic structures. The relationship between black holes and galaxies is most evident in the striking correlations observed between the mass of a central supermassive black hole and properties of its host galaxy's bulge, such as stellar velocity dispersion and luminosity. These correlations suggest that the growth of black holes and galaxies are regulated by common processes or by feedback mechanisms that link their evolution. The existence of such tight relationships across a wide range of galaxy masses and types implies a fundamental connection between the physics governing black hole accretion and the processes that drive galaxy formation and evolution. These scaling relations provide crucial constraints for theoretical models attempting to explain the coevolution of black holes and galaxies throughout cosmic history. The coevolution of black holes and galaxies is driven by a complex interplay of physical processes, including gas accretion, star formation, and various feedback mechanisms that can either stimulate or suppress further growth. When galaxies accrete gas from their surroundings, this material can both form stars and feed the central black hole, creating a connection between the growth rates of both components. However, as the black hole grows, it can produce energetic feedback through radiation, jets, and winds that heat or expel gas from the galaxy, potentially limiting further star formation and black hole accretion. This self-regulating cycle creates a delicate balance between the growth of the black hole and the evolution of its host galaxy, establishing the observed correlations between their properties. The role of mergers in driving both black hole and galaxy growth represents a crucial aspect of their co-evolutionary dance. When galaxies merge, their central black holes eventually sink to the center of the newly formed system through dynamical friction, forming a binary pair that may ultimately coalesce. These merger events can trigger intense bursts of star formation and black hole accretion as gas is compressed and funneled toward the center of the system. The gravitational waves produced during the final merger of black holes provide a direct signature of these events, which have been detected by observatories like LIGO and VIRGO. Each merger represents a significant step in the cosmic evolution of both black holes and galaxies, contributing to the growth of the most massive systems observed today. Observational evidence for the coevolution of black holes and galaxies comes from studies of galaxies at different cosmic epochs, revealing how the relationship between black holes and their hosts has evolved over time. In the early universe, galaxies and their central black holes were often undergoing rapid growth, with high rates of star formation and black hole accretion observed in systems such as submillimeter galaxies and quasars. As the universe aged, the growth rates of both galaxies and black holes declined, with the most massive systems reaching a state of relative quiescence. This cosmic evolution suggests that the co-evolutionary processes that link black holes and galaxies have been active throughout cosmic history, though their relative importance may have changed over time. Theoretical models of black hole and galaxy co-evolution attempt to reproduce the observed scaling relations and cosmic evolution through simulations that incorporate the relevant physical processes. These models typically include gas cooling, star formation, black hole accretion, and various feedback mechanisms that regulate the growth of both components. Modern cosmological simulations can now track the formation and evolution of thousands of galaxies and their central black holes within the context of the expanding universe, providing detailed predictions that can be compared with observational data. While current models have achieved considerable success in reproducing many observed properties, challenges remain in explaining the full range of galaxy and black hole populations observed in the universe. The feedback processes that link black hole and galaxy evolution operate through multiple channels, each with different effects on the surrounding medium. Radiative feedback from the accretion disk around a black hole can heat gas and ionize atoms, potentially preventing cooling and suppressing star formation. Mechanical feedback from jets and winds can inject energy and momentum into the interstellar medium, driving outflows that carry gas away from the galaxy. These feedback mechanisms can operate on different spatial and temporal scales, creating a complex network of interactions that regulate the co-evolution of black holes and galaxies. Understanding the relative importance of different feedback processes remains an active area of research in astrophysics. The co-evolution of black holes and galaxies has profound implications for our understanding of the universe's large-scale structure and evolution. The energy injected by black holes into their surroundings can influence not only their host galaxies, but also the broader intergalactic medium, affecting the formation and evolution of cosmic structures. This feedback can heat gas in galaxy clusters, preventing excessive cooling and star formation in the central regions, and contribute to the enrichment of the intergalactic medium with heavy elements produced by stellar evolution. The influence of black holes thus extends from the scales of individual galaxies to the largest structures in the universe, demonstrating their profound impact on cosmic evolution. The study of black hole and galaxy coevolution has been revolutionized by advances in observational technology, particularly in the realms of multi-wavelength astronomy and high-resolution spectroscopy. Modern telescopes and instruments can observe galaxies and their central black holes across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, providing comprehensive views of these systems. Spectroscopic observations allow astronomers to measure the motions of stars and gas in galaxies, revealing the presence and properties of central black holes. These technological advances continue to transform our understanding of the coevolutionary relationship between black holes and galaxies, revealing new details about the physical processes that govern their growth and development. The diversity of galaxies and their central black holes observed in the universe reflects the complex history of their coevolution over cosmic time. Some galaxies host relatively small black holes for their size, suggesting that feedback processes may have limited black hole growth, while others contain black holes that appear more massive than expected based on their host galaxy properties. This diversity may arise from differences in the accretion histories of black holes, variations in the efficiency of feedback processes, or the influence of the large-scale environment in which galaxies evolve. Understanding the origins of this diversity represents a key challenge for theoretical models of black hole and galaxy coevolution, as it requires explaining not only the average relationships, but also the scatter and outliers observed in the population. The connection between black holes and galaxies extends to the chemical evolution of the universe, as both play crucial roles in the production and distribution of heavy elements. Stars in galaxies produce elements heavier than hydrogen and helium through nuclear fusion, while the energetic processes near black holes can also contribute to nucleosynthesis through various mechanisms. The feedback from black holes can then distribute these elements throughout the galaxy and into the intergalactic medium, enriching the cosmic gas with the building blocks for planets and life. This chemical evolution represents an important aspect of the coevolutionary relationship between black holes and galaxies, connecting the microphysics of stellar and black hole processes to the large-scale chemical composition of the universe. The cosmic timeline of black hole and galaxy coevolution reveals distinct phases of activity that have shaped the universe we observe today. In the early universe, during the epoch of peak cosmic star formation and quasar activity, galaxies and their central black holes were growing rapidly, with frequent mergers and high accretion rates. As the universe aged, the growth rates of both galaxies and black holes declined, with the most massive systems reaching a state of relative quiescence, while smaller systems continued to evolve. This cosmic evolution reflects the changing availability of gas for accretion, the decreasing frequency of major mergers, and the cumulative effects of feedback processes that regulate growth over cosmic time. Theoretical models of black hole and galaxy coevolution continue to improve as our understanding of the relevant physical processes deepens and computational capabilities advance. Modern simulations can now incorporate increasingly sophisticated treatments of gas dynamics, star formation, black hole accretion, and feedback processes, allowing for more realistic modeling of the co-evolutionary relationship. These simulations have revealed that the co-evolution of black holes and galaxies is a highly nonlinear process, with small changes in initial conditions or physical parameters potentially leading to significantly different outcomes. The continued development of these models promises to provide deeper insights into the physical mechanisms that drive the cosmic dance between black holes and galaxies. Observational studies of black hole and galaxy co-evolution have revealed that the relationship between these components may evolve with cosmic time, with the scaling relations observed in the local universe potentially being different at earlier epochs. Some studies suggest that black holes in the early universe may have been more massive relative to their host galaxies than those observed today, implying that black hole growth preceded galaxy growth in some systems. Other research indicates that the correlation between black hole mass and galaxy properties was already in place at very early cosmic times, suggesting that the co-evolutionary processes establishing these relationships were active even in the early universe. These findings continue to drive theoretical efforts to understand the origins and evolution of the black hole-galaxy connection. The co-evolution of black holes and galaxies represents one of the most fascinating and complex stories in cosmic history, illustrating the intricate web of physical processes that shape the universe. From the formation of the first galaxies and black holes in the early universe to the diverse population of systems observed today, this cosmic dance has unfolded over billions of years, creating the rich tapestry of cosmic structure we observe. The study of this relationship connects seemingly disparate areas of astrophysics, from star formation and stellar evolution to accretion physics and feedback mechanisms, revealing the deep underlying unity of cosmic processes. As our understanding of black hole and galaxy co-evolution continues to deepen, we gain not only insights into these specific phenomena, but also a greater appreciation for the complex, interconnected nature of cosmic evolution. Generate paragraphs with a maximum length of 800 characters each. If a paragraph exceeds 800 characters, split it into multiple paragraphs, ensuring each new paragraph is no longer than 800 characters. Chapter titles for structure only. Remember, the chapter titles provided in the outline are strictly for your organizational reference and should not appear within the narrated script itself. Transition smoothly into the content of each chapter without mentioning its title. Consistent flow and tone. Maintain a consistent narrative voice and relaxing atmosphere throughout this part. Transitions between chapters should be gentle and unobtrusive, preserving the calm, immersive quality established in last part. Spoken content only. Include only the words that will be spoken aloud in the script. Do not write any stage directions, sound effect cues, or visual descriptions. Every line of the script should be text that the narrator will read out loud. No images. Do not include any images or image references in the script text. No URLs. Do not include any website URLs or external links in the script. Paragraphs must have 4 sentences or more. Next step. Script writing instructions, new part. Use the part outline provided at the bottom. Base the script strictly on the completed plan from last step, following the chapter structure provided for this part. Each chapter listed under this part should be fully expanded into detailed narrative text, consistent with the established flow from last part. Adherence to script criteria. Follow all previously defined script criteria explicitly. Maintain a relaxing, slightly mysterious tone Write at a slow narrative pace, suitable for relaxation. Use only spoken text, without including chapter titles, visual descriptions, stage directions, images, or URLs. Seamless. Continuation from last part. Ensure that this part continues smoothly and naturally from where last part ended, maintaining continuity without providing a conclusion. The listener should feel like this part is seamlessly picking up from the previous section. Seamless transition. This part to next part. This part should also end without a final conclusion. It should flow naturally into next part, maintaining continuity so that the listener feels the documentary is still in progress. Target length and reading speed. Create content suitable for a slow narration speed of approximately 130 words per minute, achieving roughly 1 hour and 30 minutes of narration, approximately 11,700 words. Please now proceed to generate the full script content for this part of the documentary titled Spacetime Torn: How Black Holes Reshape the Cosmos. Part 5. Chapter 3. Quasars, the brightest objects in the universe. In the vast cosmic tapestry, there exist celestial phenomena of such extraordinary brilliance that they outshine entire galaxies, appearing as brilliant beacons across the unfathomable distances of space. These cosmic powerhouses, known as quasars, represent some of the most energetic and distant objects ever observed in the universe, challenging our understanding of physics and pushing the boundaries of astronomical observation. The discovery of quasars in the 1960s marked a pivotal moment in astronomy, revealing a previously unknown class of celestial objects that would ultimately transform our conception of the cosmos and the role of black holes within it. These enigmatic sources of light have captivated scientists and stargazers alike, offering glimpses into the extreme conditions that exist near supermassive black holes and providing valuable clues about the early universe. The journey to understanding quasars began in the late 1950s, when astronomers started detecting powerful radio sources that could not be easily identified with any known optical objects. These mysterious radio emissions prompted further investigation, leading to the identification of the first quasar, 3C273, in 1963 by Martin Schmidt at Caltech. When Schmidt analyzed the light from this object, he discovered that its spectrum exhibited unusual emission lines that were significantly redshifted, indicating that 3C273 was located at an enormous distance from Earth, yet still appeared bright enough to be seen with relatively modest telescopes. This revelation was astonishing, as it meant that 3C273 was producing more energy than hundreds of galaxies combined. Yet this energy was originating from a region smaller than our solar system, defying conventional explanations and challenging the very foundations of astrophysics. The extraordinary luminosity of quasars presented a profound puzzle for astronomers, as no known stellar process could account for such tremendous energy output from such a compact region. Various theories were proposed to explain the nature of these cosmic powerhouses, including supermassive stars, chains of supernova explosions, and even exotic new physics beyond our current understanding. However, as more quasars were discovered and studied, a consensus gradually emerged that the most plausible explanation involved accretion onto supermassive black holes, with gravitational energy being converted to radiation with remarkable efficiency. This theoretical framework suggested that quasars represent a particular phase in the evolution of galaxies, during which the central supermassive black hole is actively accreting matter at a high rate, producing the spectacular display of energy that characterizes these cosmic phenomena. The central engine powering quasars consists of a supermassive black hole surrounded by a swirling disk of gas and dust known as an accretion disk, as matter in this disk spirals inward toward the black hole. It is heated to extreme temperatures by friction and gravitational compression, causing it to emit enormous amounts of radiation across the electromagnetic spectrum. The efficiency of this energy conversion process is truly remarkable, with up to 40% of the rest mass energy of the infalling matter being converted to radiation, far exceeding the efficiency of nuclear fusion processes that power ordinary stars. This extraordinary efficiency explains how quasars can outshine entire galaxies while being powered by a region no larger than our solar system, creating some of the most luminous, persistent sources of light in the universe. Quasars exhibit a diverse range of properties, with variations in luminosity, spectral characteristics, and the presence of jets or outflows that can extend for thousands of light years. This diversity reflects differences in the mass of the central black hole, the rate of accretion, the orientation of the system relative to our line of sight, and the environment in which the quasar resides. Some quasars appear as point sources of light with little structure visible, while others show complex morphologies, including extended jets, lobes, and filaments that interact with the surrounding medium. The study of this diversity has provided valuable insights into the physical processes occurring near supermassive black holes and the factors that influence quasar activity, helping astronomers to develop a more comprehensive understanding of these cosmic phenomena. The discovery that quasars are powered by accretion onto supermassive black holes has had profound implications for our understanding of galaxy formation and evolution. Quasars are now recognized as a specific type of active galactic nucleus, representing the most luminous members of a broader class that includes Seyfert galaxies, blazars, and radio galaxies. The relationship between these different types of active galactic nuclei is primarily determined by the luminosity of the central source and the orientation of the system relative to our line of sight, with unobscured views of the central engine appearing as quasars when the luminosity is sufficiently high. This unified model has helped to explain the diverse properties observed in active galaxies and has provided a framework for understanding how supermassive black holes influence their host galaxies through various feedback mechanisms. The extreme luminosity of quasars makes them visible across vast cosmic distances, allowing astronomers to study the universe during its early stages of development. Some quasars have been detected at redshifts greater than 7, meaning we are seeing them as they existed when the universe was less than 1 billion years old. These ancient quasars provide valuable information about the conditions in the early universe, including the formation and growth of the first supermassive black holes, the enrichment of primordial gas with heavy elements, and the development of large-scale cosmic structures. The study of high redshift quasars has revealed that supermassive black holes with masses exceeding 1 billion times that of our Sun already existed when the universe was less than 10% of its current age, challenging our understanding of how these objects could have formed and grown so quickly in the early universe. The existence of quasars in the early universe has significant implications for our understanding of cosmic evolution and the role of supermassive black holes in shaping the cosmos. These ancient beacons suggest that the conditions for rapid black hole growth were present much earlier in cosmic history than previously thought, potentially involving direct collapse of massive gas clouds or unusually efficient accretion processes. The energy output from these early quasars would have had a profound impact on their surroundings, ionizing gas, heating the intergalactic medium, and potentially influencing the formation of the first galaxies. By studying the properties and distribution of quasars across cosmic time, astronomers can reconstruct the history of supermassive black hole growth and its connection to the evolution of galaxies, providing insights into the physical processes that have shaped the universe over billions of years. Quasars serve as cosmic laboratories for studying the behavior of matter under extreme conditions that cannot be replicated in terrestrial laboratories. The intense gravitational fields near supermassive black holes, the enormous temperatures and pressures in accretion disks, and the powerful magnetic fields that drive jet formation all create environments where the laws of physics are tested at their limits. By analyzing the radiation emitted by quasars across the electromagnetic spectrum, astronomers can probe these extreme conditions and study phenomena such as relativistic effects, particle acceleration, and the interaction between matter and radiation in ways that complement theoretical models and computer simulations. Each quasar, observed, provides a unique window into the physics of black hole accretion and the complex processes that occur in these cosmic engines. The variability of quasars represents another fascinating aspect of these cosmic phenomena, with many quasars exhibiting changes in brightness over timescales ranging from days to years. This variability provides valuable information about the size of the emitting regions and the physical processes responsible for the energy production in quasars. The fact that some quasars can vary significantly over just a few days implies that the emitting region must be relatively compact, as changes in brightness cannot propagate faster than the speed of light. By studying the patterns and timescales of quasar variability, astronomers can constrain the size and structure of the accretion disk, the mechanisms responsible for energy production, and the relationship between different emission components, helping to build a more detailed picture of the physical processes occurring near supermassive black holes. The jets and outflows observed in many quasars represent some of the most spectacular manifestations of black hole activity, extending for thousands of light years beyond their host galaxies. These highly collimated beams of plasma are launched from the immediate vicinity of the supermassive black hole, likely through processes involving the extraction of rotational energy from the black hole itself. The interaction between these jets and the surrounding medium creates enormous radio lobes and cavities that can be observed across vast cosmic distances, providing evidence of the profound impact that quasars can have on their environments. The study of quasar jets has revealed important insights into the mechanisms of particle acceleration, the role of magnetic fields in shaping these outflows, and the feedback processes that regulate the co-evolution of black holes and their host galaxies. Quasars also play a crucial role in the cosmic ecosystem through their influence on the surrounding intergalactic medium and the regulation of star formation in their host galaxies. The intense radiation and powerful outflows from quasars can heat gas to extremely high temperatures, preventing it from cooling and collapsing to form new stars, a process known as quasar feedback. This feedback mechanism is thought to be essential for explaining the observed properties of massive galaxies, including the correlation between black hole mass and galaxy properties, and the relatively low star formation rates observed in the most massive galaxies. By studying the impact of quasars on their environments, astronomers can better understand the complex interplay between black hole growth and galaxy evolution, and how these processes have shaped the universe over cosmic time. The study of quasars has been revolutionized by advances in observational technology, particularly in the realms of multi-wavelength astronomy and high-resolution imaging. Modern telescopes and instruments can observe quasars across the electromagnetic spectrum, from radio waves to gamma rays, providing comprehensive views of these systems and the various components that contribute to their emission. Space-based observatories like the Hubble Space Telescope, Chandra X-ray Observatory, and James Webb Space Telescope have provided unprecedented views of distant quasars, revealing details about their structure, composition, and the environments in which they reside. These technological advances continue to transform our understanding of quasars and their role in cosmic evolution, with each new discovery bringing fresh insights into the physics of these cosmic powerhouses. The connection between quasars and the growth of supermassive black holes represents a fundamental aspect of galaxy evolution that continues to be actively researched. Quasars are now understood to represent a phase in the life cycle of galaxies during which the central supermassive black hole is growing rapidly through accretion of surrounding material. This phase of intense activity is typically triggered by events that bring large amounts of gas toward the center of the galaxy, such as galaxy mergers or instabilities in the galactic disk. As the black hole grows, it produces feedback that can eventually limit further accretion and star formation, leading to a decline in quasar activity and the transition to a more quiescent state. Understanding this cycle of activity and quiescence is essential for explaining the observed properties of galaxies and their central black holes throughout cosmic history. The study of quasars has also revealed important connections between these cosmic phenomena and the large-scale structure of the universe. Quasars are not randomly distributed throughout space, but tend to cluster along filaments and sheets that define the cosmic web, reflecting the underlying distribution of matter in the universe. The correlation between quasar positions and the large-scale structure provides valuable information about the relationship between black hole growth and the cosmic environment, suggesting that the formation and evolution of these systems are influenced by their surroundings. By mapping the distribution of quasars across cosmic time and space, astronomers can reconstruct the history of structure formation in the universe and gain insights into the physical processes that have shaped the cosmic web over billions of years. As our understanding of quasars continues to deepen, these cosmic phenomena remain at the forefront of astronomical research, representing some of the most extreme and informative objects in the universe. The study of quasars connects seemingly disparate areas of astrophysics, from black hole physics and accretion processes to galaxy evolution and large-scale structure formation, revealing the deep underlying unity of cosmic phenomena. Each new discovery in the field of quasar research brings fresh insights into the physical laws that govern the universe and the complex processes that have shaped cosmic evolution over billions of years. The ongoing exploration of these cosmic beacons promises to reveal even more about the nature of supermassive black holes, the early universe, and the fundamental connections between black holes and galaxies that define the cosmic landscape we observe today.